Good morning. So we're going to wait just a very short amount of time, and then we're going to start. We have a lot to do today. We have to finish the course material, go over homework, review for test 2. So 3 very important things to do. Okay, so we're just going to wait a short amount of time for people who get here soon. Okay, so while we wait just a very short time, prepare your questions for the rest of homework 8 after 6.1.4, homework 9, and homework 10. Okay, so if you have questions about them, just think about what you would want to ask. I'm going to ask that question very soon. Okay, so G-Lin is now here. Okay, so let's start. Okay, so are there any questions about the rest of homework 8 after section 6.1.4, homework 9, or homework 10? So we have the rest of homework 8 after this section. So these two sections here. There's homework 9 and homework 10, which is just these few questions. So really, it's kind of like a little shorter assignment along with 2 short sections here. So it's kind of like one long assignment. Any questions about any of these problems? Okay, so we're gonna keep going now. Okay, so today's announcements. I'm assigning homework 11 today. So if you go on Blackboard, I have the solutions to homework 11 in the file. So you can go on Blackboard, go to homework, and then I put up the solutions, not just the answers. I typed up how to do each of the problems for homework 11. Okay, so I'm aware the test is tomorrow, and so there's one more homework assignment, and so I'm assigning it today, but you can do it and then look at the answers online. Okay, so it's only a 6-week course. I have to hurry, and so we need that. This is the best way to do that. We have a review for test 2 at the end of this class, which means this class is extended for the review. Okay, all classes have the video online as long as I'm able to post it, which so far I've been able to post every video on YouTube without a problem. So you'll most likely be able to look at the review on video, okay, once I post it later today with that, if there's no problem. So we also have a final for the review after test 2 is administered on Thursday. Okay, so class on Thursday is also extended, and that's for a review for the final after test 2 is done. Okay, a reminder, test 2 is tomorrow, the 12th, right? And a reminder, the finals on the last day of class, which is next Monday on the 16th. And also a reminder, practice questions for both test 2 and the final can be found on Blackboard in the test menu bar link, and then in the correct folders in that page. Okay, so these are all the things you need to know today, and so they're right here. And so if you go on Blackboard later, you go to this lesson, you can look at these announcements again. Okay, so this is the last chapter of the course, and so we're going to finish the material for the course today. Okay, so this is chapter 7 on multivariate distributions. And so these are functions that don't depend on just one random variable. They depend on multiple ones. So up to this point, we've only dealt with probability distributions, which depend on one random variable. And in chapter 7, we look at ones that depend on more than one. Okay, so 7.2 is on multivariate distributions. And 7.2.1 is on multivariate probability functions. Okay, so let's look at the first definition 7.1. The multivariate probability function, okay, of the discrete random variables x1 to xn is the function defined by this. So this is the PDF with n inputs, and it's the probability that the random variable x1 is equal to little x1, and the random variable x2 is equal to little x2, and so forth, up to and including the random variable xn is equal to little xn. For all possible values, little x1, little xn of capital 1 to capital Xn, respectively. Okay? So it's just a probability that your n random variables take on these corresponding n values. Okay? Example 7.1. The experiment is rolling a die and then tossing a coin. Okay, so first you roll a die, the numbers are 1 through 6, and then you toss a coin, and it's either heads or tails. Okay, x1 is the value on the die, so x1 can take values from 1 to 6 inclusive, and x2 is the number of heads, so it's a number of heads. So when you toss the coin, if heads comes up, you get a 1. If tails comes up, you get a 0. Okay, so x2 can be 0 or 1. Find the joint probability function of x1 and x2. Okay. Well, first let's make an observation that events x1 and x2 are independent events. These two events do not depend on each other, right? When you roll the die, it has no effect on how you toss the coin. And when you toss the coin, it has no effect on how you roll the die, right? So these two actions are independent of each other and have no effect on the other. And so therefore, we can find the joint probability function of x1 and x2. And it's simple. The probability that capital X1 equals little x1 and capital X2 equals little x2 is equal to the probability that capital X1 is equal to little x1 times the probability capital X2 is equal to little x2, right? Because these two events are independent of each other. And so what's the probability that x1 would take any of its possible values? It's 1/6, right? When you roll a die, every outcome has a 1/6 chance of happening. And so this probability is 1/6 for all x1 values from 1 to 6 inclusive. And then x2 could take on a value of 0, 1, and the probability of each is just 1/2, right? Probability of getting 1 heads in a toss of a coin is 1/2, and the probability of 0 heads in one toss of a coin is also 1/2. And so you just multiply 1/6 times 1/2, and it's equal to 1/12. And so the PDF here of x1 and x2, our first example of a multivariate probability function, is equal to 1/12 for all possible inputs of x1 and x2. Okay, for x1 from 1 to 6 inclusive, and x2 from 0 to 1 inclusive. Okay, and this depended on the fact that events x1 and x2 were independent events, in which I could say that the probability of both of these events happening is the product of their respective probabilities. That you need the fact that they're independent events in order to justify this equal sign right here. So that equal sign right there, again, is justified by this observation, that the two events x1 and x2 are independent of each other. Okay, example 7.3. Let x equal the number of outgoing calls. Let y equal the number of outgoing long distance calls. It's outgoing local calls. X is local, y is long distance during a 5-minute period. The joint probability function of x and y is given by the following table of values. Okay, and it defines the function f of x comma y. Okay, so there are several ways to express a function, and I think I already told you this, right? It's not just an equation. You can express a function in lots of ways. You can express a function as a set. You can express a function as with an equation. You can express a function in words. You can also express a function as a table. Okay, as long as it completely describes your function, there's no ambiguity, right? Then you can express it with a table. If you say for each input what the output is, then you're telling the reader what that function is, right? And so you don't have to write a function a certain way. You're expressing the same thing in just another way. So this table is expressing our PDF f of x comma y, because for each input of x and y, we give an output And that outputs the probability that capital X takes on the value 0 through 4 inclusive, and the value capital Y takes on a value from 0 to 2 inclusive. So for instance, what is the probability that there are 3 local calls, right? 3 local calls, X equals 3, and 1 long distance call, Y equals 1. That probability is 0.02, okay? During a 5-minute period. So this table tells you that. Okay, so for part A, you want to use the table here. What is the probability that there are exactly 2 local and 2 long distance calls? Okay, we just ask yourself, what should X be, and what do you want X to be, and what do you want Y to be? Well, this is equal to probability that capital X equals 2, that the number of local calls is 2, and capital Y equals 2, the number of long distance calls is 2. See? And the table tells you that the probability that X is 2 and Y is 2 is 0.01. And so the answer is 0.01. Make sense? Very simple. You just have to be able to take your starting probability that you want to find, expresses the probability of a joint probability function as a multivariate probability function, either writing it this way on the right or this way on the left. They both mean the same thing. They're both the same. And so I wrote it as equaling to this because this is more expressive of what we're doing, right? And so this is saying more, and so you can see what I'm doing. And so that equals 0.01 according to the table. Okay, part B, what is the probability that there are more than 3 outgoing calls? Okay, well, it just says outgoing calls, right? It doesn't say long distance or local. And so X plus Y is the total number of outgoing calls during this 5-minute period. We're staying with the 5-minute period the whole time. So what we want to know is what is the probability that X plus Y is greater than 3, right? What is the probability that the total number of outgoing calls is greater than 3? Okay, so well, when is X plus 3 greater than 3? It's either 2 plus 2. So we want the probability that X equals 2 and Y equals 2, plus the probability that X equals 3 and Y equals 1, right? Plus the probability X equals 4 and Y equals 0, plus the probability X equals 3 and Y equals 2, plus the probability X equals 4 and Y equals 1, and plus the probability that X equals 4 and Y equals 2. Okay, well, so looking at this again, I said, well, what about X equals 1, right? We don't have any X equals 1s. But if X equals 1, then the most Y can be is 2, and 1 plus 2 is 3, and you want more than 3, right? So X has to be at least 2. In order for your sum to reach at least 4, to get to larger than 3, you need X to be at least 2. Now, when X is 2, Y has to be 2. So you have X equals 2, Y equals 2 here. And that's the only one for X equals 2. And then X can't be 0, 1 in order for the sum to be greater than 3. This is the only one that works when X is 2. And then you consider, well, X is 3, Y is 1, X is 3, Y is 2, X is 4, and then you have all these, okay? So it's really on the right side of the table, okay? And so the table just tells you the values. So f of 2 comma 2 is 0.01 right there. F of 3 comma 1 is 0.02. F of 4 comma 0 is 0, which I just wrote it here. 2, 4, 6, 2, 4. There's 6 numbers here. So that's F of 4 comma 0. F of 3 comma 2 is 0.01. F of 4 comma 1 is 0.01. And F of 4 comma 2 is 0 again. Okay. And so that's that. Right. So 2, 2 is 0.01. 3, 1 is 0.02. 4, 0 is 0.01. Oh, 4, 0 is 0.01. There we go. Okay. So it's right. And then that's the 0.01. And 4, 3, 2 is 0.01. 4, 1 is 0.01. And 4, 2 is 0. So it matches up perfectly. So these 6 are in this order. And you add them up. The number of hundredths is 1 plus 2 plus 1 plus 1 plus 1. That's 1, 3, 4, 5, 6. So you have 6 hundredths. So that's the probability that there are more than 3 outgoing calls. C, what's the probability of no outgoing local telephone calls? Okay, I went directly to the values of the function. We want the probability that there are no local. The local ones are the values x, right? So to have no local telephone calls, you want x to equal 0. So if x is 0, then y could be 0, y could be 1, or y could be 2, and you add them. And so you add these probabilities, you have 0.23 plus 0.11 plus 0.03 right here. And so you add that and you get 0.37. So that's the probability of no local telephone calls when the probability x equals 0. So this is equal to the probability that x equals 0, and y could be anything. So I'm gonna write y being anything as being 0 less or equal to y, less or equal to 2. Okay. And there we go. So x has to be 0, y could be anything. See, just there. Okay, so the next section is 7.2.2, which is on multivariate cumulative distribution functions. This is just the cumulative distribution function for a probability function with more than one random variable. Okay, definition 7.2. The multivariate cumulative distribution function of the random variables x1 to xn. I'm not going to underline it because I don't want it to, the underline to go over the indices here. So that is the function capital F defined by this. So capital F of x1 to xn is the probability that the random variables capital X1 to capital Xn are at most little x1 to little xn respectively, where the little x's are finite values. Okay, this just says that the little x's are finite. Okay, and I'm saying I from 1 to n, so that way I include all n of the little x's here. Okay, if two random variables are involved, the multivariate cumulative distribution function is called the joint cumulative distribution function. So I'll underline this. When the word joint is there, that means that there are exactly two. Okay, but the joint cumulative distribution function is just a multivariate cumulative distribution function. Okay, it's just a multivariate one where the number is that there's two random variables. Okay, but multivariate in general could be 3, 4, 5, 6, 7, 8, 100, 1,000. Even 2 would still be a multivariate one. A joint, the word joint just makes it very specific that there are two of them. Okay, example. Consider the random variables x and y of example 7.3. Find capital F of 2, 1. Example 7.3. Example 7.3 was this example with this table, okay? Where x is the number of local outgoing calls, y is the number of long distance outgoing calls during a 5-minute period. Okay, so x local, y long distance, there's the table. Okay, so we want to find here capital F of 2, 1. Find capital F of 2, 1. And so that equals the probability that capital X is at most 2 and capital Y is at most 1. Okay, simple. So what is the probability that capital X is at most 2 and Y at most 1? So in order for capital X to be at most 2 and Y to be at most 1, then what we want are the top 6 values on this table. These 6 values that are around here. See these 6 here that I'm putting my cursor around? These 6 mean that X is at most 2 and Y is at most 1. And so it's F of 0, 0 plus F of 0, 1, blah. F of 0, 0 plus F of 0, 1 plus F of 1, 0 plus F of 1, 1 plus F of 2, 0 plus F of 2, 1. Okay, and so you have those 6 values there. And so that's just what I wrote here, maybe in different order. So F of 2, 1, 2, 1, 2, 0, 1, 1, 1, 0. I did this way. 2, 1, 2, 0, 1, 1, 1, 0, 1, 0, 1, 0, 2, 1, 2, 0, 1, 1, 1, 0, 0, 1, 0, 0. So I added those 6. Yeah. And so you take out the values there and you have these 6 corresponding probabilities. So you have 0.05 plus 0.11 plus 0.11 plus 0.23 plus 0.11 plus 0.23. There we go. And so you add them up and you get 0.84. Okay, I was just adding them again to make sure. So this is 0.84. Okay, and so that's capital F of 2 comma 1. All right. The next section is 7.2.3 on multivariate probability density functions. So definition 7.3, for continuous random variables, capital X1 to capital Xn, they're jointly continuous. If they're jointly continuous, if there is an integrable function f such that the probability that capital X1 and capital Xn, or most little x1 and little xn respectively, is equal to this this integral, this repeated integral. Okay. So you're just finding like the area underneath an n-dimensional a curve that exists underneath the value of a function that exists in that has n variables. Okay, so f of t1 to tn is the value of a function with n variables. Okay, it's not okay, and so so now you integrate not just with one integral but with n integrals. Okay, and so this is like finding the space underneath this function, right? If you had two variables, right? If you had two variables, a joint probability density function, right? I don't want to use joint. Joint, it has a different meaning here. Jointly continuous, okay? Jointly and joint sounds very similar, but they're different meanings, okay? But if you had a function with two variables, right? The value of the function would exist in 3 space, and you would kind of have like a surface, okay? So a function of 2 variables, like f of t1, t2, would be like a surface existing in 3 space, and then the double integral would be like the volume underneath that surface, okay? So if you have a function with 1 variable, like f of t1, it's a curve, right? And the integral is the area under that curve. If you have a function of 2 variables, it might be like a surface. It might be, it doesn't have to be. It could be like a surface, and the space underneath that surface is volume, 3-dimensional, right? And so for, let's say, an n variable function, you could have an n-dimensional object existing in n plus 1 dimensional space, and then the space underneath that function would be an n, and the amount of space would be in n plus 1 dimensions, okay? And so that integral, these n integrals would be telling you the amount of space underneath that function, okay? Amount of space in 1 dimension is length, in 2 dimensions it's area, in 3 dimensions it's volume, and then there are, so in small dimensions we have common names for a measure of the amount of space something takes up in that dimension. But in general, this is just the amount of space underneath the value of this n variable function that just exists possibly in n plus 1 dimensional space. Okay, so that's the this is the definition of jointly continuous n random variables that are okay. So if you start with continuous random variables x1, xn, this collection of n continuous random variables is jointly continuous if there is an integrable function f such that you can express this probability always as being an iterated integral of this form. Okay, the function f is the multivariate probability density function of the random variables. Okay, the thing we defined earlier, this little f is the same as that little f. Okay. Okay. When 2 continuous random variables are involved, the multivariate probability density function is called the joint probability density function of the random variable. Okay, I already said that. Okay, some important facts. By definition 7.3, the definition 7.3 right here. If x and y are jointly continuous random variables with probability density function f of x comma y, right? Then 1, the joint cumulative distribution function of x and y is capital F of x comma y, which this says, which is this integral. Okay, so you're just integrating up to this fixed value at little x, and you're also integrating up to this fixed value of little y. Okay, and this double integral is from your joint, excuse me, your joint probability density function, and this is for any finite values little x and little y. Okay, so this follows immediately from the definition. For values, okay, for values a capital X between A1 and B1 and capital Y between A2 and B2, the probability that X and Y are between or in those intervals, open intervals, is equal to this double integral, right? So you're just integrating from A1 to B1 with respect to X, and you're integrating from A2 to B2 with respect to Y. So it's important that the order of dx and dy corresponds with the order of the limits of integration here, right? So A1 to B1 is for X. And so that's why dx is first, because the inner integral has limits of integration from A1 to B1 that correspond with the range of possible X values, right? Then the outer integral goes from A2 to B2 because the range of Y values is between A2 and B2. And the outer d here is dy. And so the dy has to do with the outer integral. Dx is for the inner integral. Okay. 3. If C is a region of points x, y in the plane, and P of x, y in C denotes the probability that the random variable x and y will take on the respective values little x and little y, so that x of y is a point in region C, then P of x, y in C is equal to the double integral over C of f of x, y dx dy. Okay, so basically, okay, so I think this is easy to see that, but maybe not. So if you have the xy plane, here x values, here's y values. I really want to get rid of that arrow. Okay, so you have x and y, right? X, y axis. And so let's say you have a region here, and we call it region C, right? And so you can look at points. What we care about are points that exist inside of this region C. So these are points whose coordinates are little x and little y, such that the point is in this region C, right? Okay, and so what we care about is this region. We care about the region inside of C. And I could highlight this too, right? But I just don't want to, I want you to be able to read the coordinates of that point. And so if you want to know the probability, right? If you want to know the probability that that x, this is the notation, x, y, capital X is capital X, capital Y, here's little x, little y, that ordered pair in C, well, that's saying what is the probability that when you choose a capital X value and a capital Y value, the corresponding values little x and little y sit inside this region C that I've colored in red. And so then you just what you want to do is just, you kind of want to infinitesimally add up the PDF f of x, y across this entire region C. And so your PDF is little f of x, y, because it's a joint probability density function, because you have exactly two continuous random variables, capital X and capital Y. And so what you want to do is you want to double integrate that. And so that way you're pretty much adding up the values of this function over the entire region C. And this notation where you just put a C underneath this means that you choose the limits of integration appropriately. So that way you're integrating over C. Okay? That makes sense? Okay, so that's the integration over the region C, and probably only defined if the integral exists. So so there are some integrals that exist and some that don't. And an integral existing again means that its value is finite, right? If the value is infinite, it doesn't exist. So as long as this double integral exists, you can calculate, you get a finite number, then this probability is well defined. Okay? Okay. And its value will have to be between 0 and 1 inclusive, but that we have our PDF already, right? This is already a PDF, and so you know that you should be able to integrate over the entire space, and it should equal 1. And so there's no way this double integral, if you have a correct little f, there's no way this double integral could be more than 1 by the fact that this is already a PDF. Okay, 4. If capital F of x comma y is a cumulative distribution function of x and y, then the joint probability density function is given by little f of x comma y, which is the second derivative of capital F with respect to x and y. So it's d2 capital F dx dy. Okay. At all values x and y where the partial derivative is defined. Okay. So if you have a partial derivative, okay, for both with respect to both x and y, then little f is this. Okay, these 4 statements can be extended to more than 2 jointly continuous random variables. And so in this case, I consider 2. Okay, so I said if x and y are jointly continuous random variables with PDF f of x comma y. Instead of choosing 2, we chose 3 or 4 or 5 or any finite number. We can extend these 4 statements to appropriately, we have to change the number of integrals, we have to change how many times we take the derivative, right? Make with minor changes that are hopefully obvious, you can extend these statements to include any number of random variables, continuous random variables. Okay. Okay. Jointly continuous random variables. Okay. They have to be jointly continuous. Example 7.7. Suppose x, y are continuous random variables with joint probability density function f of x comma y, which is equal to this. Okay, so only when x is between 0 and 2 and y positive do you have a possibly non-zero non-zero probability. 0 everywhere else. A, find the joint cumulative distribution function of x, y. Okay. So we're going to split this up into 4 cases. Okay, and so for each case, we're going to find capital F. Case 1 is for x less than or equal to 0 and any y. If x is less than or equal to 0 and y is anything, then capital F of x comma y, you have the double integral here. But now little f, when x is at most 0, well, x does not fall in this range of values. And so that means that little f has to be 0. And so little f is 0 throughout this entire region. And so that means that when you double integrate 0, you get 0. And so capital F has to be 0 if x is less than or equal to 0 and y is anything. That's case 1. That's easy. Case 2. Let's say y is less than or equal to 0. If y is less than or equal to 0, then y also does not fall in the region of y greater than 0. And x can be anything. And so that means little f has to be 0. And so capital F is equal to this, which is equal to this, where you substitute little f for 0, because little f has to be 0 for these values of x and y. And so when you double integrate 0, you get 0. So capital F is 0 in case 2 also. Case 3, there's more work now. So for case 3, let's just look at the obvious situation that x is between 0 and 2 and y is positive. Okay? If x is between 0 and 2 and y is positive, then we have possibly non-zero value for capital F. So capital F is equal to this by definition. And then we substitute. So little f is definitely this, right? You would say it's this, it is. But now how do we integrate? Okay, so so first I just rewrote these are the limits, right? But now we don't have to double integrate over everything here because we know that it's 0 everywhere else outside of this region, right? And so if it's 0 everywhere else, then we only need to integrate from 0 to little x, little to 0x, where little x is between 0 and 2. And we only need to integrate with respect to y from 0 to this little y value. So we have some positive little y value. We only need to integrate from 0 to that value because everything less than 0, the function to the left is 0. And so if you integrate over a function that's 0 and 0, right? Okay, so now when you double integrate this, notice that you can separate the s and the t expression. So you have 1/2 s because there's no t expression here. And then there's e to the negative t, which you put here. And so now you can just integrate both of them and multiply by their integrals. That's just how it sets up here. And then this is equal to, well, if you integrate this and multiply it by, this is a definite value, right? And so is this. Okay, this is an expression of y, and this is an expression of x. And so when you multiply this expression of y and this expression of x, you get 1/4 x squared times 1 minus e to negative 2. Okay, so maybe I'll show you on the whiteboard how that works out. Okay, but this is calculus, and so calculus is a requirement. You should know it, so you should be able to integrate this. So I would not say that this is necessarily something I'd want to go over, but I will. Okay, so I showed you already how to do that. So what I want to focus on is how you get these integrals, right? So this is the integral from 0 to y of e to negative t dt. Okay, and so, right, how do you find an integral? If we're going to do this the long route, we let u equal e negative t. And so we're going to just use a substitute. Actually, there's more than one way we can do this. And I don't want to do it that way, but I could. Let's choose u equals negative t. Then du is equal to negative dt. And so by u substitution, well, first I'm going to say it's negative this e to negative t times negative 1 dt. I just multiplied by negative 1 twice, which keeps the value the same, right? If you multiply something by negative 1 twice, you're multiplying by 1, and so the value is unchanged. And so now this is equal to negative the integral from 0 to y of, well, e to the, we're going to do it with respect to u. U is negative t, so this is e to the e to the u for e to negative t. Du is negative dt, negative 1 dt is negative dt, which is du. And so we make this substitution. Now the corresponding values of u for these values of t, if t is 0, u is 0. And if t is y, then u is negative y. And so now we have this. And so this is the same as the integral from negative y to 0 of e to the u du. Okay, and now this is equal to an antiderivative of e to the u is itself, right? And so you evaluate that from negative y to 0. And so that's equal to e to the 0 minus e to the negative y. E to the 0 is 1, so this is 1 minus e to the negative y. Okay, so I just showed is that the integral from 0 to y of e to the negative t dt, that value, right, this thing, is equal to 1 minus e to negative y. Okay, and then you just calculate the other integral, and the other integral is the definite integral from 0 to x of 1/2 SDS. Okay, so again, you're using calculus here, so I can't reteach you all calculus. So you need to remember how to calculate integrals. And so this is just one example of calculating integral. And so you need to be able to calculate other integrals also that don't have time to show you in class. Okay, so you have 1/2, and then if you integrate an antiderivative of s is s squared over 2. So you have s squared over 2, and you evaluate from 0 to x. Okay, and so now the 1/2 can move out. So this is a 1/4. This is a 1/4 s, and then s squared is still being evaluated from 0 to x. And so this is equal to 1/4 times, well, when you plug in x, you get x squared, minus plug in 0, you get 0 squared. X squared minus 0 squared is x squared, so this is x squared over 4. Okay, so the value of that depth integral is x squared over 4. Okay, so now what I showed is that this depth integral is equal to x squared over 4. And so in that proof for case 3, you multiply this depth integral times this one, and what you get is this times this. So you have 1/4 x squared times 1 minus e negative y. And so that's how you get it. You just calculate each of these and you get these and you multiply them. Okay. So let's go back. Use substitution. Yes, Kishan, right? So I use substitution right here, right? This was where the use substitution happened, right? That was use substitution. Oh wait, no, though. I made it here is where I use substitution, right? That was the use substitution. Okay, so that was use substitution for this equal sign, and I justify I used this u, right? Okay, good. So that answers your question. Okay, right. So so that's how you get 1/4 x squared times 1 minus e negative y here. This times this on the other screen. Case 4 is for x greater than equal to 2, y positive. So if x is greater than equal to 2 and y is positive, you have capital F is equal to this double integral. Well, if you're integrating over x here, and x is greater than equal to 2, then you integrate from 0 to 2, because you're integrating from negative infinity to x, where x is greater than equal to 2, and it's only non-zero for x between 0 and 2. Okay, so if you're integrating from 0 to little x, and it's only non-zero between 0 and 2, you're integrating between 0 and 2. Does that make sense? Okay, so again, what we're doing is you're integrating, here's the real number line, right? And so the function is only non-zero between little x equals 0 and little x equals 2. Right, here's little x equals 0, here's little x equals 2. Everywhere else, the function is 0. Right, red for 0. And I guess green for non-zero. Okay, so it's only non-zero here. These are little x values. Right, and so where it's red is where the function little f could be non-zero. You're also considering y, right? So there's also y. But if little x only between 0 and 2 is the PDF non-zero. And so when you integrate with respect to little x, where is little x? So little x from case 4 is greater than or equal to 2. Okay, so little x is some value here, which is greater than or equal to 2. I'm not saying the range is greater than 2. I'm saying I'm choosing a point x that is greater than or equal to 2, right? And so if you integrate from negative infinity to little x, where x is greater than or equal to 2, and it's only non-zero between 0 and 2, then instead of integrating from negative infinity to little x, right, of f, what you would want to do is you would want to integrate. Well, there's also another integral, right, for y, right? Right, and you would need dummy variables here, which is what I do. So you have st for the dummy variables for x, y, respectively, right? But you would not want to integrate all of this. So instead, you would just integrate from 0 to 2. So for x, it's going to be from 0 to 2. Because for x, you're going to integrate from negative infinity to x, right? But the function's only non-zero here. So if you're integrating from negative infinity to here, and this doesn't matter, and this doesn't matter, right? This doesn't matter, and this doesn't matter. Only this matters. And so you only integrate from 0 to 2. And so that's f of s comma t. That's with respect to the dummy variable s. S is called a dummy variable because we're really talking about x. But if you're integrating to x, you can't use x again, and so you technically use little s to represent the values of x changing. Okay, and then and then y is assumed positive, and so if y is positive, then you're just going to integrate from 0 to y. Because y is positive and y is negative, doesn't matter. So you have that. Okay. Okay, so this is for capital F of x comma y. The point of this was just to depict the what this integral should be, right? This is what I was caring about on this page, right? I wanted to focus on these limits of integration and why they're between 0 and 2. Okay, so that was the point of this page. Okay. Okay, so this is from 0 to 2, and that's 0 to y, and this is the PDF there, right? It's 0 everywhere else, and so we only care about when the PDF is that. And so now, when you integrate, you can separate them because you have separate expressions for s and t. So you have the 1/2 s. I put the 1/2 s here, and I put the e negative t here, and you find this expression of y times this expression, which is a number, and you get 1 minus e negative y. Okay. And that's it. So then this is case 4. Okay. And so what we did was we found capital F over all possible values x and y, because these 4 cases exhaust all possible choices of x and y in R2. Okay. And they're separate. There's non-overlap between these 4 regions, but they all exhaust all possible choices. Okay, so for part B, it's find the probability that capital X is at most 1 and y is at most 2. Well, that's equal to capital F of 1 comma 2. And that's equal to now, so capital F of 1 comma 2. So if x is 1 and y is 2, we're in this region here, because this is for x values between 0 and 2 and y positive. Okay, and it does not work here. It doesn't work here because x has to be greater than 2. It doesn't work here because y would have to be less or equal to 0. It doesn't work here because x has to be less or equal to 0. So the only there's exactly 1, which is what we want, and that's capital F of 1 comma 2. Okay, so for this, you plug in x equals 1 and y equals 2 into this expression. So what you have is this expression where x is 1 and y is 2. So it's 1/4 times 1 squared times 1 minus e to negative 2. And so now it's 1/4 times 1 minus e to negative 2. And that's that probability. The probability that x is between 1 and 2 inclusive and y is between 3 and 4 inclusive is this double integral where x ranges from 1 to 2 and y ranges from 3 to 4. And so now, so again, the PDF here is 1/2 x to e to negative y. And you do this integral, and when x is from 1 to 2, you have that, and from y from 3 to 4, it's positive. So it's this thing throughout. And so you just find this double integral and you get that value. Okay. Okay, so how do you find this definite? How do you find this double integral? So I'll calculate it for you. So let's go to the whiteboard. But this is just review because calculus is assumed to be known here. Okay. Okay, so you have a double integral of 1/2 x e to negative y dx dy. Okay, and it's from 1 to 2, 3 to 4. So x is ranging from 1 to 2, y is ranging from 3 to 4. And so you want to find the value of this integral. So let's put an equal sign here for that. Okay, I'm going to separate the x terms and y terms. And so to separate the x terms, this is the definite interval from 1 to 2. It's only because I can separate the x and y that I can do this. This is equal to 1/2 x dx, which is the value of one definite integral, times the value of another definite integral, which is the integral from 3 to 4. Well, it's 1/2 x dx, so e to negative y dy, in which we already calculated the second integral. Okay, so this 1/2 just moves out of the integral. And so now this is 1/2 x squared over 2, evaluated from 1 to 2. This is the first definite integral, times the value of the second definite integral. And so I'm just going to make it so the brackets are not. There we go. Made nicer brackets for you. And now e to negative y is negative e. I guess I'll just do an antiderivative of e negative y is negative e to negative y. Okay, and you can use substitution to show that. If you take the derivative of negative e negative y, you get negative e negative y. That's positive e negative y. Okay, so this is an antiderivative of this integrand, and you're evaluating it from 3 to 4. And so this is equal to the 2 in the denominator is a 1/2. So this is 1/2 x squared, and you can move the 1/2 out and you get 1/4. So this is 1/4 times x squared evaluated from 1 to 2. That's x squared evaluated. So I guess I'm going to put a lot of steps here. This is x squared evaluated from 1 to 2. And it's times 1/4, and that's still the value of the first definite integral. This is times negative e negative y. The negative sign is a -1. And so it's a -1 times e to negative y, where it's being evaluated from 3 to 4. And then, so I'm just putting a lot of steps here. I wouldn't want to normally do that. 1/4, so here is 1/4 still for that 1/4. X squared evaluated from 1 to 2 is now plug in 2, get 2 squared, minus plug in 1 squared. 1/4 times 2 squared minus 1 squared. And so that's the value of the first bracket, times now in the second bracket, you have a -1 here. And then you have e negative y, you plug in 4, you have e to negative 4 minus, and then e to negative, plug in 3, you have e to negative 3. Okay, and so when you calculate this, you get 2 squared minus 1 squared is 4 minus 1, which is 3. So that's 3/4. And there's a negative sign here. So this is negative 3/4. And you might think there's a problem with that negative sign, which you should, well, you shouldn't, but you want this to be positive, right? And it is. But okay, so you have 4 minus 1, which is 3, 3/4, negative 3/4. So you have negative 3/4 times e to negative 4 minus e to negative 3. And so what you should see is that this value is positive. This has to be positive. That's one thing you should see. You should also see that this is actually positive, because e to negative 4 is smaller than e to negative 3. E to negative 4 is 1 over e to the 4th, and you're subtracting e to negative 3, which is 1 over e cubed, right? Which one's bigger? E to the 4th is bigger than e cubed. That means the denominator of this one is larger than the denominator of that one. That means this fraction is smaller than this one. So you're taking a fraction that's smaller and you're subtracting one that's bigger. So that means that this quantity is negative, right? That's a side note, that this e to negative 4 minus e to negative 3 is negative. And so you're taking this negative 3/4 and multiplying by this negative, and that's why the answer is positive. To make this better, you could say you could also write 3/4. You can multiply each by -1. So -1 times negative 3/4 is 3/4, and then times this times -1 would be e to negative 3 minus e to negative 4, right? And so why would you do this? It just so it looks nicer, because now you're not, in a sense, by looking at this, you might be tricking the reader into thinking this is negative, but the reader should know. But if you multiply them each by -1, you're showing the reader very easily that you take 3/4 and you're multiplying it by this, which is positive. It's certainly easier to make sense out of that. Okay, and so this is equal to that. And so that's exactly what we have in the Word document. that this double integral is equal to the value of that expression. So this is equal to 3/4 times e to the negative 3 minus e to the negative 4. So that's equal to 3/4 times e to the negative 3 minus e to the negative 4. Okay, and then that's how you do it. Okay, so next is example 7.8. Let x and y be continuous random variables with joint probability density function little f of x comma y, which is equal to this. Okay, so if x is between 0 and 1 and y is between 0 and 1, not inclusive, strictly between them, you have this expression and you have 0 everywhere else. Let C be the region on points, be region of, let C be the region of points x comma y in the plane such that x plus y is less than 1. Find the probability x comma y is in C. Okay, so let's draw a picture of this situation. Okay, so little f is only non-zero if little x is between 0 and 1 strictly, and little y is between 0 and 1 strictly. Okay, so let's look at the whiteboard. So we have the x and y plane, right? And the PDF is only non-zero when little x is between 0 and 1. These are little x values, and these little y values, and little x is between 0 and 1, not inclusive, and little y is between 0 and 1, not inclusive, right? And so only in this region, right? Only here can little f of x comma y take on a non-zero value, not including the boundary, right? So not including the boundary of this rectangle, only not including the boundary of the square, only inside the square is the PDF non-zero, right? So again, let's look at word, right? For x between 0 and 1 strictly and y between 0 and 1 strictly, we have this, and it's 0 everywhere else. Okay, let C be the region of points in the plane such that x plus y is less than 1. Find the probability that x and y take on values where the corresponding little x, little y is in this region C. Okay, where little x and little y satisfy that inequality. Okay, so we have x plus y is less than 1. That's the region of points. Little x, little y, such that x plus y is less than 1. So we have little x plus little y has to be less than 1. Well, that's equivalent to the inequality y is less than 1 minus x. You just subtract both sides by x, you get x plus y minus x is y, and 1 minus x is 1 minus x. So this is equivalent to the inequality y less than 1 minus x. Let's look at y equals 1 minus x. So y equals 1 minus x would be, well, y equals x is the diagonal. Y equals x is the diagonal like this. Y equals negative x, according to in pre-calculus, y equals negative x is this. Y equals 1 minus x is taking the negative x curve and adding 1 to it. It's the same as negative x plus 1. And so y equals negative x plus 1 is this curve. That's y equals 1 minus x, right? That's y equals 1 minus x. Now, for y less than 1 minus x, the y less than 1 minus x, I'm going to denote by light blue. So little y less than 1 minus x, which is equivalent to x plus y less than 1. The same solution as x and y. Little y less than 1 minus x would mean that the y value is below this graph. So for instance, if x was 1, right? If little x was 1, then 1 minus 1 would be 0. So if little x is 1, then that would say y would have to be less than 0. right? So if y is less than 0, it's below, it's a negative y value. It would be below that point. For any point in this curve, consider the little x that would correspond to a point on this curve for some y, right? For y equals 1 minus x, you would have for a fixed value of x, a point on this curve, you want y to be smaller than the y value that would make them equal. And so that means that y would have to be below the curve. Okay, anything on the line would make them equal, which would be wrong. And if it's above it, y would then be greater than 1 minus x. So little y, all the x points, x, y that satisfy y less than 1 minus x are the points below this line. Okay, where I'm including this region here. Okay. Okay, so that's our region C. Okay, and so what we want is the probability that our point is in the region C. Well, the probability our point x comma y is in the region C would then have to be only considering the region in this triangle here, right? So you agree with me that all we care about is that. I'm not going to draw a line because it's not including the boundary. So you agree with me that all we care about is this region. It's the overlap of where the PDF is positive and in the region C. And so this probability is going to be this is equal to the probability that probability is equal to the double integral over the region C of little f of x comma y. Dx dy. Right, we have to consider points that where the PDF, we want only where the PDF is positive and it has to be region C. Okay. And so when you take this double integral, you want to take the double integral of this region. And so when you take the double integral, then you want the x values, let's say, okay, we're going to do y. So then what you have is the PDF f of x comma y. There's more than one way to do it oftentimes. So sometimes there is more than one way, sometimes there isn't. So let's integrate with respect to x first and then y. So we're going to integrate with respect to x first from 0 to 1 minus y. So when you integrate from 0 to 1 minus y, right? Actually, let's use the colors a little more creatively here. I'm going to use two colors here. One is going to be pink for the x, and the other one, oh, pink is too close. Let's go use x for that, and red for that. So for x, we're going to go from 0 to 1 minus y. So if you're integrating with respect to x from 0 to 1 minus y, you're kind of looking at the heights of a rectangle, right? Where we're going from x equals 0, from left. Nope. 0 to 1 minus y. So it's horizontal. Oh, right. Okay, right. So x. There we go. Now I got it. All right, sorry. Here. Okay, so you have x equals 0 to 1 minus y. So it's the horizontal one. Let me draw that with my hands. Okay, so when you do a double integral, you can think of in of a rectangle going in the appropriate direction. And so this rectangle is denoting the fact that the x values are ranging from 0 to 1 minus y, right? This is x equals 0. That's when x equals 0. This is x equals 1 minus y, right? This is the line y equals 1 minus x. So for x, x is equal to 1 minus y. So this is from x equals 0 to x equals 1 minus y. And so that's why you're integrating from 0 to 1 minus y. And then for y, well, these rectangles are ranging from the bottommost rectangle to the topmost one. And so the y values are ranging from 0 to 1. And so y is ranging from 0 to 1. And so that means you're integrating from 0 to 1. So that's calculus, being able to do a double integral and express a region as integrating a double integral over a two-dimensional region as knowing how to do that. Okay, and so in this example, that's how you do that. And so now you calculate this double integral, and the PDF f of x comma y is what it was defined to be in the problem. It's this thing, okay? And you have the integral from 0 to 1 minus y and 0 to 1 of that. And so now you take the double integral there and you calculate it and you get 5 over 24, okay? Let's keep going. 7.2.4 is on marginal distributions. So definition 7.4 says let x, y be discrete random variables with joint probability function f of x comma y. The marginal probability functions of x and y respectively are given by, this is for a discrete. So the marginal probability function of x is this, and the marginal probability function of y is that. And it's just saying that to find the marginal probability function of x, you sum over all possible values of y of f of x comma y. Okay? The marginal probability function of x is the probability that capital X equals x, but there is still other random variables. Okay? In this case, there's a second one, y. And so you would actually define the probability x equals little x, you would sum f of x comma y over all y. It might be counterintuitive that the marginal probability function of x involves summing over y. But when you sum over y, you're keeping x fixed. And so you're finding the probabilities of f of x comma y as y changes, so that you find all the ways in which x equals some fixed value, little x. Okay, and the marginal probability function of y is the sum over x of f of x comma y, because to find the probability that capital Y equals a fixed value little y, you fix little y here, and then you add up all the f of x comma y's as little x ranges over all its possible values. That way you find all the ways in which capital Y can be little y by adding over little x, f of x comma y. Okay, so those are marginal probability functions of x and y, this thing and this thing respectively. B, let x, y be continuous random variables with joint probability density function little f of x comma y. Okay, good. The marginal probability density functions of x and y respectively are given by, but this is for continuous, right? Keep in mind that this is for continuous. So I'm italicize the word continuous here, and we'll italicize the word discrete there, because that's why we have different equations for what has the same name, because they're not the same thing. They're for different types of random variables. Okay, so for continuous random variables, the marginal probability density functions of x and y respectively are given by these two equations. Okay, the marginal probability density function of x, where x and y are continuous random variables, is integrating from negative infinity with respect to y of f of x comma y. This is very similar to this case. Instead of adding over discrete possible values, a discrete set, you're adding over a continuous set, which means you're integrating. And the marginal probability function of y, instead of adding over a discrete set of values, little x, you're adding over a continuous set of values for x here. And so you're integrating from negative infinity to infinity because you're kind of infinitesimally adding all possible values of x. All possible values of x sit somewhere in the interval from negative infinity to infinity. And so you would normally take a subinterval, you would integrate over a subinterval that normally. but maybe not always. Okay. And note the probability of a less than x less than b is probably a less than x less than b, and y is between negative infinity and infinity, right? And so this would equal to the integral from negative infinity to infinity and integral from a to b of f of x on y dx dy. And then that would be, you could switch the limits of integration. And so now the y could be in the inside, and you can integrate from negative infinity to infinity here, and then a to b in the outside with respect to x. You have to switch this, and you have to switch the integrals. So both have to be switched, otherwise it's wrong. And then this is equal to the integral from a to b, but while this thing, the integral from negative infinity to infinity of f of x comma y dy, that's f sub x of x, right? So this thing in parentheses here is f sub x of x. And so that's how we have this is equal to the integral from a to b of what's in the parentheses, which is f sub x of x from this equation, dx. And dx is from here. And so it just shows that the probability that a less than x less than b is equal to the integral from a to b of f sub x of x dx, which makes sense, right? Because f sub x of x is the probability that capital X equals little x. And so if that's the probability that capital X equals little x, then the probability that capital X ranges from a to b should be the integral from a to b of that. Okay? This implies that the probability of a less than x less than b is equal to that, right? Because this is then equal to that. Okay. Examples. So we already pretty much had this for single variable functions, right? For single variable PDFs. But when you have more than one variable, your PDF is actually in terms of multiple variables. And so you can't write f of x here, because f is a probability density function that depends on more than one random variable. So you have to use the marginal probability function of x and y to look only at one single variable. Okay? Example 7.14. Find the marginal probability density function of random variable x of example 7.5, and find the probability that x is greater than 2. So example 7.5. Where's example 7.5? So 7.3. Okay, I just give you all the information. Okay, so the joint probability density function of x and y is this. Okay, so that's the joint probability density function of x and y. Find the marginal probability density function, right? Because this is what we want to find, right? Okay, so I just give you the PDF here. There you go. And so this is equal to this by definition, because it's with the x one. So you're integrating with respect to y. If you're integrating with respect to y, the only y values you care about are y positive. Excuse me. Okay, so this is the PDF. This is the PDF, and you're integrating there. Okay. Okay, so it turns out that this integral is equal to this. So all I did was so you have this, which is dy, and I substitute f of x comma y for that. And if you integrate this, you get e to the negative x. Okay, so I'll quickly show you that. Okay, so when you integrate from negative infinity to infinity of e to the negative x, e to negative y, dy. Okay, let's calculate it. So it's with respect to y. So the e to the negative x moves outside of the integral, and now you have the integral of e to the negative y dy. But the way we defined it, so going back, what values of y do we care about? So going back to the problem, what values of y do we care about? We only care about y positive, right? So we only care about y positive. But now we want to integrate from 0 to y, where y is positive, but we have to use a dummy variable because y is the thing we want to go to. It's not really, so here we use a dummy variable t to represent y. So now this is equal to e to the negative x, right? And so now an antiderivative of e to the negative t is negative e to the negative t, and you evaluate from 0 to y. And so when you evaluate that, it's e to the negative x times, and then you have a negative 1 here for the negative sign, and then you have e to the negative t, and so value from 0 to y. So it's e to the negative y minus e wait, oh, sorry. And so then, oh, sorry, we're integrating from negative infinity to infinity, right? Okay, and y, for y positive, you have that this is positive. So you're integrating from 0 to infinity. Sorry, so you're integrating from 0 to infinity because you have this thing for all y positive, and you're integrating to infinity. So it's actually to infinity. So this is to infinity and beyond. Okay, so just to infinity. Okay, so that just to infinity. So I can use y here, and so I'm going to use y, so it's not confusing. E to negative y dy. Okay, so you have that, and this is from 0 to infinity, and so you have a y here. So, okay, so you have negative 1. E negative y is e to negative 0, negative infinity, minus e to negative 0. Okay, I'll accept that shortcut in that step. E to negative x times negative 1 times e to negative infinity is 0. That's 1 over e to infinity. That's 1 over infinity. That's 0. This is 0 minus e to negative 0. That's e to 0, which is 1. So you have a minus 1 here. You have a minus 1 here and a minus 1 there. They multiply to 1. And so this is equal to e to negative x. Okay, so that's showing you how when you get this integral from negative infinity to infinity, how you get that's equal to e to negative x. Okay, and so that's what I did in Word. And so that's equal to e to negative x. So that thing is equal to e to negative x. And that's for x positive because of how our PDF was defined right here for x positive. Okay, that's the marginal probability density function of x. And then the probability x is greater than 2. Well, the probability x is greater than 2 since we have our and so then this is equal to, and let's just write this. Okay, this is equal to integrating from 2 to infinity of the marginal probability density function of x dx. Right, this is the probability that capital X equals some fixed value little x, and so you want to integrate that from 2 to infinity. Remember, we have more than one variable in this example, but this is now the probability that capital X equals little x. Okay, and so if you want to single that out, this little f here, this is being loose with the notation. This little f is a different function than that little f of x on y. This little f would be referring to the PDF of a single random variable, and this would also be referring to a PDF of a single random variable as opposed to this, which is 2 variables. And so that's why here, a mathematician would think that's fine, but I'm putting it here just so it's clear, and I'm not being loose with the notation by switching the meanings of f. So you're just integrating in this example with the marginal probability density function from 2 to infinity. And so since we found what that was, we found this is e to negative x for x positive. Now, since when x is greater than 2, x is positive, we know that f sub x has to be e negative x. It's not 0 there. So it's always e negative x in this interval. It's you're integrating from 0 to 2. X greater than 2. So then okay, there's two ways I could add this to 1 minus this, but I'm not going to do that. I'm going to put infinity here. Okay, so it's from 2 to infinity of e to negative x dx. And so when you calculate that 2 to infinity of e to negative x dx, the integral from 2 to infinity of e to negative x dx, that's equal to negative e to negative x evaluated from 2 to infinity and so then that's you now plug in infinity, e to negative infinity minus e to negative 2 being, and see you can use that shortcut. It's negative 1 times e negative infinity is 1 over e infinity, which is 0. This is 0 minus e negative 2. So this is negative 1 times negative e negative 2. Negative signs cancel, and you get e to negative 2. Okay. All right. So it is that value. Okay. So this is equal to e negative 2. So that's equal to e negative 2. So it's just 2 to infinity there. Okay. Just same thing there. Okay. It's e negative 2, which is 0.1353. Okay. So the next section is 7.2.5. Conditional distributions. Let x, y be discrete random variables. So the probability that capital X equals a fixed value little x and capital Y equals fixed value little y is equal to the probability that x is little x naught and y is little y naught divided by the probability of y equals y naught. And so this corresponds exactly with what you think it might be from conditional probability, right? I mean, this is from conditional probability. And so this probability in the numerator is little f of x naught, y naught. That's the meaning of the multivariate probability density function, right? And then the probability that capital Y equals y naught, you can use the marginal probability density function to say this is the same as f sub y of y naught. And this is provided that the probability that capital Y equals y naught, or f sub y of y naught, is positive. Okay, provided that that's positive, or I mean, I'm saying the same thing, just using different notation. I'm not saying two different statements, or that expression is positive. That's what that means, right? Because we want the denominator to be, we don't want it to be 0, okay? We already know the probability can't be negative because it's a probability density function. And so because we're using probability density functions, that can't be negative. And so if we're saying it, if it's already not negative and we're saying it can't be 0, then that means that the condition is that it's positive. Okay, f sub x of x given y naught, then this is notation for the probability that capital X equals x little x given that capital Y equals y naught. So this notation is just, you don't have to write x equals and y equals. You can just write little x y naught, where it's understood that little x is a value of capital X and y naught is a value of capital Y. Okay, we're using the letters. We're using corresponding letters. We're not using y, little y, to denote a value of capital X. We're not using little x naught to denote a value of capital Y. We're matching our lowercase letters with our capital case letters. And so since we do that, we're good. Okay. Okay, so this is the probability. So okay, so f sub x of x given y naught, right? So this is probably at capital X equals little x given y equals y naught. Okay, so okay, and so we just see here is that okay, so we already know that this is the conditional sorry, this is the conditional probability function of x given y equals y naught. Okay, so this lowercase x is now meaning something slightly different because of this vertical line. This is the notation for this. Even though there's a lowercase x here, it's meaning something slightly different because of the vertical line. Okay, so this is now the probability that capital X equals this, given, because of the vertical line, that y equals y naught. And this is equal to the little f of x comma x naught over f sub y of y naught. Okay, and so that's the name of it. It's called the conditional probability function of x. I'm going to underline of x also, because it matters with respect to what variable you're thinking of, given y equals y naught. So this is part of it also, though I don't necessarily want to underline it. I guess you can still see the 0 there. Okay, I'm going to underline. Okay, given y equals y naught. Okay, so f sub x of x given y is equal to this, where just instead of y naught, we're using y. So that's why that's there. And then f sub y given x is a symmetry. And so all it's changing now is instead of the y's being here, it's x's. Okay, and again, this is if these two things in the denominator are positive, right? You can never divide by 0 for a fraction to make sense. A regular fraction makes sense. And so we want that these two things are positive. Okay, example 7.15. Okay, so let x, y be continuous random variables of example 7.8. F sub x of x is equal to this. And so now we have our PDF in example 7.8. And so something is here. I'm doing it. 7.3, example 7.8. So example 7.8 was this one, where we had this PDF for x and y between 0 and 1. And that's the one where we had the region C. So this is from x from 0 to 1, and we had this probability equal this thing, right? So, okay. Okay, so now this is our PDF, right? But x is between 0 and 1, and y is between 0 and 1. And so if we're integrating with respect to y, then y is going to range from 0 to 1. And this is for any fixed value little x, only also between 0 and 1. Because if x is not between 0 and 1 that we fix, we already know it has to be 0. So, and so now you just integrate this. The value of this integral here is x plus 1/2. Okay, and the marginal probability function of y is you integrate over the real line with respect to x. And now you're only considering y between 0 and 1 because everywhere else it's 0. And so now you're going to integrate from 0 to 1 also because you only care about between 0 and 1. This integral with respect to x is equal to this expression of y, because you have y in the integrand, which you say is a constant. And so when you integrate with respect to x, y, treating y as a constant, you get an expression of y. Okay, and so that's for A. We're finding the marginal probability functions of x and y respectively. Okay, for B, for y strictly between 0 and 1, we're going to find this function, which is the conditional probability function of x. And so now this is equal to this expression. And so that's why we have this expression here. But just instead of y naught, it's y. So here, here, okay. So then that's this. Well, that's equal to, well, what is f of x? F sub y of y is equal to this, which we already found. And it's only oh, okay, here we go. For y between 0 and 1. Okay, for y between 0 and 1, right? For y between 0 and 1, you have that f sub y of y is this. But then for f of x comma y, where's our f of x comma y? f of x on y is the original PDF in the problem, right? I'm just going to scroll and show you that it's a PDF. I'm not showing anything here. There, right? That's the PDF. 2xy plus 3 half y squared. Okay, that's for x and y, which are both between 0 and 1. That's just the PDF, and so I'm plugging it in. That's the PDF, and y has both x and y have left. Here's the PDF in the numerator, and that's x that's between 0 and 0 and 1. Also, you divide this by this, you simplify it. You divide the numerator down by y because they both have a common factor of y. So a y cancels, and you remove a y in the numerator as a factor, and remove a y as in the denominator as a factor, and you get this fraction. There's 0 everywhere else. Okay, for x between 0 and 1, the marginal probability function of y is equal to this by definition. This is still the PDF of the function, so that's why the same thing is in the numerator. But now the marginal probability function of x is different. It's x plus 1/2, right? Because of here, so you have x plus 1/2 in the denominator. You're just doing numerator divide by denominator of the things. The denominator of the things you calculated in A. The numerator is the given PDF in the problem, and this is for x between 0 and 1, but also for y between 0 and 1 because it's 0 everywhere else. In C, you want to find the probability that x is between 0 and 0.5 inclusive. That's just the integral from 0 to 0.5 of the marginal probability function of x, as stated earlier when I said that this, right? Probability that x is between two values is an integral from the first value to the other of the marginal probability. And this applies for y also. So if y was between two values, you would integrate the marginal probability function of y. Okay. So for C, you're integrating the marginal probability function of x from 0 to 0.5, and that function is x plus 1/2. As you integrate that, and you get that. Here, you integrate from 0 to 0.4, like I was saying, of the marginal probability function of y. And this is the marginal probability function of y. It's y plus 3/2 y squared. In this, from 0 to 0.4, that falls within 0 to 1. And so that is the PDF there. And you calculate this step integral and you get 0.112. And for D, you want to find the probability x is between 0 and 0.5 given y is equal to 0.3. And so okay, and so now here, this is just, so when you do this integral, you're going to integrate from 0 to 0.5 of the margin of the conditional probability function of x given y equals y0. Okay, and so that's because you see this vertical line here that corresponds with this vertical line. What you care about is a range of x values here. Then what you care about is the given, is not the given. This range here. This is the given to the right. This is this. And so you're integrating with respect to these values from 0 to 0.5. And it's f sub x because this is x here. And then this value is changing from 0 to 0.5. And then this is staying fixed at 0.3 because y is 0.3 is a given. And so now you have this function here. We have f sub x already of x given y. It's this really complicated expression. F sub x of x given y is equal to this. And so f sub x of x given 0.3 is you plug in 0.3 for y there. And so you plug in 0.3 for y into that expression to get this function here. And when you do that, you get this. That's this expression. That's this expression plugging in 0.3 for y. So the 0.3 here, you plug in for y, you get 2x plus 3/2 times 0.3 over 1 plus 3/2 times 0.3. And so that expression, when y equals 0.3, that's this. And so now you get this, and you're still integrating from 0 to 0.5 with respect to x. And so you can do that. You integrate that with respect to x from 0 to 0.5, and you get that value there. Okay, and we're almost done. And then the material for the course is done, and then we'll have a review for test 2 immediately following and extend class for that. Okay. Remember, homework 11 is due tomorrow, and all the answers are on Blackboard, and so you can refer to the answer. So I'm explaining to you how to do the problems without needing another class to do that. The probability that y is between 0 and 0.4 and x equals 0.2 is now integrating this. Similarly, because y is going from 0 to 0.4, 0.2 is fixed as a value of x. You plug in the expression for f sub y of y given x, except you plug in x equals 0.2. And then you integrate that with respect to y from 0 to 0.4. Then you get 0.0914. Okay. This is section 7.2.6, the multinomial distribution. Again, we're almost done. Let nk be positive integers. Let p1 to pk be numbers such that the sum of those p's is 1 and each p is between 0 and 1 inclusive. The multinomial probability function f is defined by this function. For integers x1 to xk greater or equal to 0, such that the sum of the x values is n. Okay. Okay, so this is a probability function. Okay, so the probability of exactly x sub I occurrences of the outcome a sub I from I equals 1 to k is equal to the probability that x1 happens little x1 times, capital X2 happens little x2 times, and and xk happens little xk times. Well, the p's are the probabilities of these things happening. So if x1 happens little x1 times, you would want to multiply p1 x1 times. If x2 happened little x2 times, you would want to multiply the probability p2 x2 times, and so forth, up to including p sub k to the x sub k times, to the x sub k, right? But that's only if the order is that, if the order stays the same. You can change the order of these occurrences. And so this quantity is denoting all the arrangements, all the ways to arrange these occurrences of these events. Okay, and so that's why you have n factorial divided by the product of those factorials, because it's all the number of ways of arranging these occurrences, x by occurrences of the outcome a sub I. Okay, so that's a probability function. It's called the multinomial probability function. This is another function, the bivariate normal distribution. So let mu1, mu2, sigma1, sigma2, and p be constants, with sigma1 and sigma2 positive, and p between -1 and 1. The function f of x, y is equal to that for x and y finite is the bivariate normal probability density function. Okay, you do not need to memorize this for test 2. Okay. Is the bivariate normal probability density function. You won't need to know the value of that for the test. Okay, 7.3 is independent for test 2. Okay, I'm not talking about the final. I'm talking about test 2. Okay, you don't need to know. You don't need to memorize this expression. Okay, and that's called the bivariate normal probability density function. 7.3 is on independent random variables. This is the last page. Okay. Definition of independent random variables. So for definition 7.8, we have x1 to xn be random variables, discrete or continuous, with probability functions f sub 1 of x1 to f sub n of xn respectively, and multivariate probability function f of x1 to xn. The n random variables are independent if this multivariate probability function is equal to the product of these functions for all values little x1 to little xn of capital X1 to capital Xn respectively, except at points of discontinuity. Okay, so except the points of discontinuity, you can ignore these points of discontinuity, but if you have equality everywhere else, you can say that these n random variables are independent. So these n random variables are independent if that equation happens, okay, if it holds. Okay, if you could say this thing is equal to product of those things. Okay, so let's look at an example of where it happens. So example 7.17, x1 is the value in a die you roll, and x2 is the number of heads from one coin flip. We already said that these two are independent events, right? When you roll a die and you flip a coin and count the number of heads, neither has any effect on the other, right? Rolling a die has no effect on how many heads you get from flipping a coin. Flipping a coin and recording number of heads has no effect on the value of the die when you throw it. Okay, so f sub 1 of x1 is the probability that x1 equals little x1. That's 1/6, right? Because the probability of each possible value is 1/6, right? This was obvious before, but when you see these indices, you might get a little confused, right? The f sub 1 of x1 just means it's the probability, the regular PDF of a single variable of the single variable x1. Okay, so f sub 1 of x1 is the regular PDF for x1. F sub 2 of x2 is the regular PDF for x2. F sub n of xn is the regular PDF for xn. Okay, so these indices are just being used. Before we use f, now it's f1. The reason for the indices is just so that we differentiate between the PDFs of these n random variables, right? We have n random variables. We can't just write f of x1, f of xn, because then we'd only be talking about different inputs. We want different actual PDFs for each of the n different random variables. So that's why we denote the subscripts just to differentiate between the PDFs for those n random variables. Okay, so f sub 1 of x1 is the PDF for the first random variable. F sub 2 is the PDF for the second random variable. Okay, and that's the probability x2 equals x2. And that's 1/2, right? Because the probability of 1 head is 1/2, probability of 0 heads is 1/2, right? There's only two choices, heads or tails. Okay. That implies f of x1 comma x2 is equal to 1/12. Okay, which is 1/6 times 1/2, which is f1 of x1 times f2 of x2. So we showed is that f of x1 comma x2 is equal to f sub 1 of x1 times f sub 2 of x2. Okay, if you do the experiment, you see that this is equal to this. It's 1/12. 1/12 is equal to 1/6 times 1/2, and that's equal to this times this. Okay, and so saying that this is equal to this times this means that x1 and x2 are independent because of this definition. We said that n random variables are independent if you can express f of this as the product of these little f indices. And so here we said the f is equal to f1 times f2 for all x1, x2. Okay, so we have this equation. And this is for n variables. For this problem, it's 2. So we're applying this equation where n is 2. And so we get f of x1, x2 is equal to f sub 1 x1 times f sub 2 x2. We stop here. We stop at the first 2 because there's only 2 here in this problem. Okay, if there were 3, then we would have a product of 3 things equals f x1, x2, x3. Okay. Okay, so that implies x1, x2 are independent by definition. This is by definition. Okay. And so now x1, x2 is independent is equivalent to saying that the probability of A and B is equal to the probability of A times the probability of B, where event A is capital X1 equals little x1, and event B is capital X2 equals little x2, right? Because what does A intersection B mean for this A and this B? It means x1 equals little x1 and x2 equals little x2. So the probability that x1 equals little x1 and x2 equals little x2 is equal to the probability that x1 equals little x1 times the probability of x2 equals x2. This is just another way of writing this equals this. Okay? The probability of A intersection B is this probability. The probability of A times the probability of B is f1 times of x1 times f2 of x2. Okay? A intersection B would be like, remember, this is shorthand notation for x1 equals little x1 and x2 equals little x2. So f of that is the probability that x1 equals little x1 and x2 equals little x2. And then there's this is this. Okay? So this is just another notation for saying the exact same thing. Okay. And 7.3.3, and then we're done, is this independent random variables derived from independent experiments. Let E be an experiment, S be a sample space for E, and let X be a random variable on S, okay? And remember, a random variable is a function where the inputs are sample points in the sample space, and output is a value, right? The output's a value for each sample point in the sample space for an experiment. That's what a random variable on the sample space means, right? That's just a reminder. Okay, so E is repeated n times under identical conditions, this experiment. The random variables x1 and xn are independent random variables if xi is the random variable in the I performance of experiment E from 1 to I from 1 to n inclusive. That just means that if you're repeating the experiment n times, every time, if you're repeating the exact same experiment under identical conditions n times, and you have a random variable for the outcome of that experiment, each of the n times, right, one for each, then those n random variables are independent. And independent, again, means that the PDF, the multivariate probability density function, is equal to the product of their respective PDF functions. Okay, that would be independent. That's what it would mean by independent. And you have independence in this situation. So in this real life situation where you repeat an experiment n times and you have n random variables, one for each repeated experiment, those n random variables are independent, and you can apply this equation to that situation. Okay, that's why it matters. B, E1, En are separate and distinct experiments. So instead of repeating the same experiment, you're just given n experiments that are separate and distinct. The outcome of EI is in no way dependent on the outcome for EJ when I does not equal J. And so there's fancy notation for saying that if you take any two of these experiments, neither of them affects the outcome of the other. Okay? S1, Sn are the sample spaces for E1 to En respectively. If X1, Xn are random variables defined on S1 to Sn respectively, then they are independent random variables. Okay, so these experiments have corresponding independent random variables if their outcomes are separate and distinct. Okay? So if X1 and Xn satisfy A or B, they're independent by definition 7.8. Definition 7.8 is this definition. That's what I was saying. You have this equality, you have this equal sign. Okay, so if either of these two things happen in A or B, either you repeat an experiment n times, or you just have n experiments that are completely distinct and separate. In either of those cases, it should be obvious that you get n independent random variables. And if you can conclude that your n random variables satisfy A or B and that they're independent, you can then use this equation to relate the PDF, the multivariate probability density function, as a product of those. Okay? And that's the end of the course material. And so now that we're done, we can now review for test 2. So we're going to review for test 2 now. Give me 1 minute. I just want to blow my nose and drink some water. So we're going to start again. Actually, we're going to start again in 5 minutes. Okay? So I'm going to give extra time where I review for test 2. Okay? But we've already been here for a while. So let's take a 5-minute break, and I'll come back and I'll answer any questions you have about test 2 and all that. Okay? So I'll be back in 5 minutes. Okay, if you want to stay, you can stay. If you want to go, you can go. The video should be up on YouTube. You can also watch it later. But if you have questions, you need to be here to ask. Okay, I'll be back in 5 minutes. Okay, I'm back. All right, so hopefully you're all still there. Okay, so I see 13 people here. Uh, let's go to. I'm going to stop sharing for just a moment. I'm going to open up Blackboard. And just remind you how to access the things that you have on Blackboard. So it's hopefully been using it already. I've reminded you just before. Okay, so I got all these tabs here. Okay, so remember, so you should all see Blackboard now. Okay, so you're on the course page. You go to tests. You go to tests, and you go to test 2. You have practice questions for test 2 and answers to practice questions for test 2, right? Also under course materials, there's the table in Appendix C, right? So you need the table in Appendix C to do the homework, right? And here in the homework, these are the homeworks, right, that I've been assigning. These are the answers to homework 11 that I told you that you can refer to. Okay, so I assigned homework 11 today. After you do homework 11, these are the solutions. And so it's not just the answers. It's a full, I did this myself. I typed up how to do each problem. I went step by step on it. Okay, so this is a lot of work. So this is a full explanation. Well, I guess it's kind of the answer, but no, I write out a little more. So, okay, so you can use that. This section is just, there's all these functions and the symbols moving around. So there's really no easy way to present this. there's no way to make this look any prettier. It's going to look just like a mess anyway you write it, because you have all these weird, you have this, you have the marginal probability density function, you have the, you have just a lot's going on. But that's that's the homework right there. Okay, you can still see this, I think, right? Okay, so that after you do the assignment, you can look, you can study the solutions there. The solutions won't help you as much if you don't do them yourselves, right? If you just look at the answers, I don't know how much help. If you do it yourself, and it makes sense, then looking at that will help a lot, I think. Okay. Okay, so right, that's just explaining the homework. There's nothing discussion. The lesson, for lesson notes, I think this is important too. Um, I haven't posted yet because we're still talking. But once I have enough time to, this will be on, and you'll be able to click this link, and you'll have the notes for today's class. And make sure you know all the announcements for today's class. Also, right, the test is tomorrow. The rules for the exam are the same as the other exams, right? You need to have Zoom, download the device, at least 10 sheets of paper, all of that. And, everything you need to know, if you need to be reminded, is in these 2 files right here, right? So that reminds you everything you need to know. Also, the final, right? The finals on the last day of class. Review problems for the final are here. Answers to those review problems. I also have additional review problems here. I don't have the solutions for them. I'm not going to type up the solution. It's just way too much. Students say, what should I review for the final? Review this sheet. Then there's students who tell me they want more problems. They want a lot more problems. So that's what this is for. Okay, so this additional file is for students who want a lot of problems to study from, but it's a lot. So I don't have the solution for all of them, but on there. Okay, so but if you want a lot of problems, they're there. If you don't want to study that many, then focus on the first review sheet. Test 2 is going to be just like test 1. I mean, obviously not the same problems. That's not what I mean, but the structure is the same. There's 5 questions, each are worth 20 points. Okay. Okay, so what I was going to say. So for test 2, the review is going to be like the review for test 1. We're just going to go over the review sheet. Okay. So what I hope you did was you clicked the test 2 folder and you did these practice questions for test 2. So how many questions are on the final? So the final is going to be a test for 1 hour. So I'm not telling you the number of questions on the test. The test is 1 hour, and so it will not be too long. You'll have enough time to take the exam in an Okay. And okay, so practice questions for test 2. So now we're going to just go over that sheet. Okay. So for test 2, here. Okay, so here are the practice questions for test 2 that you can find on Blackboard on test folder test 2. Okay, so does anyone have any questions about any of these examples they want me to go over? No questions? Okay, let's just do number 1 because it involves a joint probability density function, which is kind of a new material, so I can help make sure that you understand it. Okay, so for number 1, if X is the maximum of the numerical outcomes of 2 rolls of a die, and Y is the number of tails in one coin toss, what is the joint probability density function of X and Y? Okay, X is the maximum numerical value of 2 rolls of a die. Y is the number of tails in one coin toss. So Y can take on a value of 0 or 1. X is the maximum of the numerical outcomes of 2 rolls of a die. So it's the maximum. So the maximum can be from 1 through 6, right? If they're both 1s, the maximum is a 1. If either of them is a 6, the maximum is a 6, right? And all numbers in between. So the max can go from 1 to 6, and Y is 0 or 1. What is the joint probability density function of X and Y? Note that if you roll the die twice and you record the maximum numerical value, and separately, if you flip a coin once and you denote and you find the number of tails in that one coin toss, those two things are completely independent of each other. So to find the joint probability density function of X and Y, that's little f of X comma Y, right? The joint probability density function of X and Y is little f X comma Y. And since X and Y are independent events, that's going to equal f sub 1 of X1 times f sub 2 of Y2. Okay? And so you just find the PDF for each of these separately and you multiply them and you get the joint probability density function. Okay, so let's go to the whiteboard. So this is for the review. So moving forward, everything after this in the whiteboard, whatever I write down, may not be much, it might be a lot. Everything moving forward on the whiteboard is review. So so X is rolling the die twice. I'm just to check this to make sure. X is the maximum of rolling the die twice. X is the maximum of rolling the die twice, right? X is the max of 2 dice rolls. Right? X is the max of 2 dice rolls. So if X is the max of 2 dice rolls, you have different values, right? So the PDF for that is going to be f sub 1 of X. And so what are the possible values, right? X could be 1, 2, 3, 4, 5, or 6, right? So what is you have X equals 1, X equals 2, X equals 3, X equals 4, X equals 5, and X equals 6, right? So, right, the question is, what is the probability that the maximum is a 2 for that? That the maximum 2 dice rolls is 1. The only way the max could be a 1 is if the only 2 dice rolls could be 1 comma 1, right? And then that would be 1. There's 36 different rolls, so that'd be 1 out of the total 36 rolls, where the maximum value would be a 1. Now, if the maximum was a 2, you could either have 1 comma 2, 2 comma 1, or 2 comma 2. Right? The max can't be, it has to be exactly 2, right? So there's 3 of them. So this is 3 over 36. Okay, and I guess I'm going to do 36 different ordered pairs. So then if the max is 3, you have 3 comma 1, 3 comma 2, 3 comma 3. There's a pattern though. And then you have 2, 3, 1, 3. Okay, so there's 5 of them here, where the maximum value is a 3, right? They're both 3, or 1 is a 2 and 1 is a 3, or 1 is a 1 and 1 is a 3, right? So there's 5 of them in that situation. Okay, let's try to see a pattern. So now let's see. For 4, the maximum would have to be 4, right? So you would have a middle ordered pair of 4, 4. Then you have lots of other ones. Now, let's say the first one is the larger one, right? Then you would have from 1 to 4, right? So you'd have 1 to 3 here. So you'd have 3 more ordered pairs here. By plus 3, I'm just going to say there's 3 more ordered pairs here, right? For 4, 1, 4, 2, and 4, 3. And here you would have 3 more if the first one's smaller. So you have 1, 4, 2, 4, 3, 4. So you'd have 7. So there's 7 for the maximum being 4. And then for the next one, for the maximum being 5, you have 5, 5. But now if the first component is larger than the second one, the second component can range from 1 to 4. So you'd have 4 more here. And then for the rest of them here, if the second component is larger, the first component could go from 1 to 4. And so you have 4 more there. So that's 4, 8, 9. So you have 9 of them where the maximum is a 5. And then for x equals 6, the maximum is a 6. And if the maximum is a 6, then that means that if the first component is larger, the second component will range from 1 to 5, and you have 5 there. And then if the second component is larger, this first component will range from 1 to 5 here, and so you have 5 more there. So you have 5 plus 5 plus 1, so you have 11, where the maximum is a 6. And so the PDF here, that's the PDF for the first random variable. So if you add up to make sure, you have 11 plus 9 plus 7 plus 5 plus 3 plus 1, it's 20, 27, 32, 35, 36. So these all add up to 1. And so this is the PDF for the random variable x. And the PDF for the random variable y, well, remember, y is flipping a coin once and recording the number of tails. Okay? Well, if the only possible number of tails in one coin flip is either 0 or 1. So y equals 0 corresponds to 0 tails, which is heads, and y equals 1 corresponds to 1 tails, which is flipping a tails. And so what are all the choices? You flip a coin once, there's only 2 possibilities, right? You could either have heads or tails. Right? So the heads here, there's only 1 possibility. That's 1 out of the 2 possibilities here. So there's a 1/2 chance that you roll heads out of the 2 possibilities, heads or tails. And if y is 1, you roll the tails, that's 1 out of the total 2 possible. So I'm counting here. The heads is the 1 choice out of the total 2. Here, the tails is the 1 choice out of the total two, right? So, so that's the PDF for y. And so f of x comma y, is just f sub 1 of x times f sub 2 of y. Now this equation is not always true, but it's true in this example because x and y are independent. Remember? So x and y need to be independent. And so in this example, we see that they are independent. Because they satisfy B. In our lesson, we talked about 2 ways in which you could have independent variables. Okay, so this is an example where you have 2 experiments whose outcomes are separate and have nothing to do with each other, right? These are 2 completely different experiments. And so that means that their corresponding random variables are independent. Okay, and so then that means f of x comma y equals f1 of x times f2 of y. And so you just take each of these and multiply it by 1/2. and you would get this. So this is equal to, I'm going to do this on the next page. So f of x comma y, since it's equal to f1 of x times f2 of y, is equal to, you just take each of these and multiply it by 1/2. And if y is 0 or y equals 1, you get the same thing because it's 1/2 of both. So you would just multiply each of these things by 1/2. And so because then f1 of x is this times f2 of y, which is this, you multiply each of these by 1/2. And so what you get is 1/72 for x equals 1 and y equals 0 or 1, right? Y could be 0 or 1. If y is 0 and x equals 1, it's 1/72. If y is 1 and x 1, it's 1/72. Also, 1/72 for y equals 0 when x is 1, and 1/72 for y equals 1 when x is 1, they add up to the 1/36, which you have here. Okay, and so you just do that for each of the other ones. And so this is 3/72 for x equals 2 and y equals 0 or 1. And then you have 5/72 for x equals 3 and y is 0, 1. And then you have 7/72 for x equals 4 and y is 0, 1. And then you have 9/72 if x is 0 is 5 and y is 0, 1. And then you have 11/72 if x is 6 and y is 0 or 1. Okay? And that's the PDF for that example. Let me just check here. You have 11/72. Yep, that's it. You just multiply the two, and then that's the PDF for number 1. So this is the answer to number 1. And so this is number 1 on the review sheet. And this is number
Professor.
1, still continued.
Professor, how do you get 72 again?
How do you get 72? It's 1/36 times 1/2.
Okay, copy.
And then 3/36 times 1/2, 5/36 times 1/2, so forth. Does that make sense?
Yeah, it does. Thank you.
Okay, good. Okay, so then that is the review sheet number 1. Okay, so that's going over number 1. We found the joint probability density function of x and y. Okay, let's do number 2. Let x be a discrete random variable with probability function f of x given by this. Find this. Okay, so we want to find e of this. Okay, so let's go to now for 4, 4. Okay, so for 4, 4, the +3, this +3 is referring to, so I'm following this pattern here where to the right, the first coordinate is smaller. So this would correspond to 1, 4, 2, 4, 3, 4. The +3 is saying that I want the maximum to be 4, where the first coordinate is smaller than the second. And so if the maximum is a 4, the larger one has to be 4, and the other one's smaller. And so there's only 3 numbers that are less than 4, right? 1, 2, or 3. So that's +3. Does that make sense? So you tell me, what is the +3 on the left? What do I mean by +3 on the left? Looking at these 3. For 3, I had this. So what is the plus? No, wait. I had these 2 for x equals 3. So for +3 here, the first coordinate is larger. So what are my +3 here? You can say it out loud or write in the chat, either one. So it'd be, no, it's 4, right? Here, the maximum is 4. Yeah, does that make sense? Those are the 3 ways where the first coordinate is the larger one, and the +3 on the right is the 3 ways the second coordinate is larger. And so the reason why I did that was because I wanted to see a pattern. I didn't want to write out 36 ordered pairs. Does that make sense? You agree with me, right? So if you see a pattern, you don't have to count all 30. You don't have to find where all 36 go. You look at the pattern, and then you start. You get it. Okay, that makes sense. Did I answer your question? You're welcome. Okay, so good. Okay, so then that is that one. Okay, so for number 2, we want to find this expected value. And you're given that the probability x equals 3 is 1/5 and probability x equals 5 is 4/5. You want to find that. Okay, so we go to here. Okay, so number 1, that 1 is explained fully on the whiteboard. Okay, 2, we want to find this expected value, right? Well, this is the same as e of x squared plus 3e of x plus 9. Okay, and so now you just need to, on the side, you need to, so the side work, you want to find, what's wrong with that word? Side work. Okay, so then we want to find e of x squared, right? And also looking back at the original review sheet, we want to find e of x and e of x squared. Okay. So you want to find e of x and you want to find e of x squared, and then just plug them into that equation, and you'll get e of x squared plus 3x plus 9. Okay, so e of x, let me quickly plug in my charger before I run out of charge. Okay, good. Okay, so the PDF f of 3 is 1/5, f of 5 is 4/5, right? And that's the PDF given to you in the problem. So notes, you are given in the problem that f of 3 is equal to 1/5 and f of 5 is equal to 4/5. So e of x, right, would just be 3 times f of 3 plus 5 times f of 5. And that would equal to 3 times f of 3, which is 1/5, plus 5 times f of 5, which is 4/5. And so then that would equal to 3/5 plus 4. And so that would be equal to 23/5. So 3 times 1/5 is 3/5. 5 times 4/5, the 5's canceling, you have plus 4. 4 is 20/5. 3/5 was 20/5 is 23/5. And e of x squared is just taking 3 squared times f of 3 plus 5 squared times f of 5. Okay. Remember, for a discrete random variable, e of x squared is equal to the sum over all possible values of x squared f of x. The only possible values of x are 3 and 5, right? 1/5 plus 4/5 is 1. So when x is 3, you have 3 squared times f of 3, right? 3 squared times f of 3 for x equals 3. And when x is 5, you have 5 squared times f of 5. Okay, and so now you just plug those in. 3 squared is 9 times f of 3, which is 1/5, plus 5 squared, which is 25, times f of 5, which is 4/5. And so you get 9/5 plus 25 times 4 is 100. I'm going to do that 100 and then divide by 5. That's plus 100/5. So that's 109/5. And then as a decimal, 5 goes into 120 times. There's 21 5s in 109 with the remainder of 4. So that's 25 and 4/5. Because then 21 times 5 is 105 plus 4. And 21 and 4/5 is equal to 21 because it's 21 and 8/10. So 21 and 8/10 is 21.8. So E of x squared is 21.8. And this 23 over 5 is the same as 46 over 10. 46 over 10 is 4.6. So as a decimal, it's 4.6. Okay. And so now E of x squared is 4.6 plus 3 times, I don't really like decimals, but I'm just using them now for some reason. Wait, E of x squared is 21.8. 21.8. So E of x squared is 21.8 plus 3 times 3 times E of x, which is 4.6, plus 9. Okay, and so 3 times 4.6 is 12 plus 1.8. That's 13.8. So you have 21.8 plus 3 times 4.6, which is again is 12 plus 3 times 0.6, 12 plus 1.8. That's 13.8 plus 9. Okay, so 12, 1.8, 13.8, good. So you add those up. 21 plus 9 is 30. 30 plus 13 is 43. 43 plus 0.8 plus 0.8 is 30. 43 plus 1.6, 44.6 is the answer. Okay, 30, 43, 43.8, 44.6. Good. So that's the answer. So for number 2, the answer is 44.6. Okay, so that's number 2. So if we look at the practice sheet again, okay, there's 7 problems. I don't know which one we want to go over. Anything else? Any specific problems somebody wants me to go over in the sheet? Number 4. Okay, so number 4. Let x be a discrete random variable. Okay, I'm going to do 4 first, though, because I said number 4 first. So let x be a discrete random variable with cumulative distribution function capital F of x below. So let's find each of these. So for A, it's find probably x less or equal to 3, right? Let me just see something for, let me stop the share for 1 second. Okay, I'm going to make our lives a little easier here, I think. I made this into a PDF. Okay, so I just saved the file as a PDF on my computer. That way I can write on this page. Okay, so want to find the probability x is less or equal to 3, right? That's just capital F of 3, right? So what is capital F of 3? That's the question. Capital F of 3, according to this, well, when x is 3, it's 0.2. Does that make sense? David, makes sense? Okay, good. And okay, good. So now the probability x is less or equal to 5. David, what is the probability that x is less or equal to 5?
It would be 0.2.
Good, because capital F of 5 is 0.6, right? So capital F of 5, according to how the function is defined, is equal to, because 5 is included in this half open interval, half closed interval, it's equal to 0.6. Good. Okay, so we're done with A. For, oh, we're not, that's not B. Okay, so other things. Okay, now the probability that 1 is that probability, erase those. Okay, so now the probability that x is somewhere between those two, that's the same as the probability that x is less or equal to 7.2 minus the probability that x is less or equal to 1.5, ignoring, you know, these less than whether it does or it doesn't include these endpoints, right? So this is probably x is less or equal to 7.2. It's a continuous random variable, so it's probably any one particular value is 0. That's why we can care about the endpoints or not. So this is probably x less or equal to 7.2 minus probably x less or equal to 1.5. This is capital F of 7.2 minus capital F of 1.5. And so David, what's that? So David, what's F of 7, capital F of 7.2 minus capital F of 1.5? Yeah, it's 0.6 minus 0, which is 0.6. Very good. This is 0.6, that's 0. 0.6 minus 0 is 0.6, right? 0.6 here, 0 there. 0.6 minus 0. Good. And so the probability x equals 10. Well, x is a continuous random variable. Oh, wait, I'm sorry. X is discrete. Okay, but okay, everything I've said so far is right. Okay, everything's right at this point. Okay, but it hasn't depended on that yet because we're just using values of this function. Okay, so that didn't matter. It's discrete. Okay, probably x equals 10. The probability x equals 10. Well, that's where 10 is here. Probably x equals 10 is the amount the cumulative distribution function jumps from x less than 10 to x equals 10. The jump is 0.2. It jumps from 0.2 from 0.6 to 0.8. There's a jump of 0.2. So probably x equals 10 is 0.2. Okay, that makes sense. And the probability that x is greater than 10.2. Probably the x is greater than 10.2. So I like this example on the review sheet a lot because it covers lots of different ways where, lots of different ways of thinking of this problem. This is 1 minus the probability of x less than or equal to 10.2. This is equal to 1 minus 1 minus capital F of 10.2. Well, capital F of 10.2 is 0.8. So this is 1 minus 0.8. That's equal to 0.2. That makes sense? Okay, so that makes sense. So now that's A. And then for B, find a probability function of x. So the probability function of x so for the probability function of x, we just want to say, okay, well, little f of x, what is little f of x? Little f of x is going to the values are going to correspond with jumps. So little f of x is 0, right, for x less than 2, right, because the cumulative function is 0. So that means that p of itself has to be 0 for x less than 2. Now, when x equals 2, there's a jump from 0 to 0.2. So the jump is 0 to 0.2 minus 0, which is 0.2. That's when x equals 2. Then it stays the same, the cumulative distribution function. So f is 0 here. Little f is 0 here. Actually, I'm not going to put 0 here anymore because it's going to be everywhere else. So there's then 0. At x equals 5, there's a jump from 0.2 to 0.6. So the jump is 0.4. And that's when x equals 5. So there's another jump in the cumulative distribution function, which means there's a non-zero probability for the PDF. And then for when x equals 10, there's a jump of 0.2. There's a jump of 0.2 when x equals 10. And then when x is 10.5, there's another jump from 0.8 to 1. And so the jump is 1 minus 0.8, which is 0.2. So it's 0.2 when x equals 10.5. And sometimes you would just write it like this, and you would say, okay, it's understood, it's 0 everywhere else. Or you could write 0 everywhere else. Now I would write the 0 else at the bottom. So I guess I'm going to write it at the bottom, even though there's less room. No way, there's no confusion. Zero else, because what is the else referring to? It's talking about the things I said already. So, okay, so it's zero everywhere else. If you add these, you have 0.4 plus 0.2 plus 0.2, that's 2, 6, 8, 10. So 1.0. Good. Okay, so that's the PDF. That's the probability function of X in part B. That makes sense? Okay, so that's number 4. David, that make complete sense? Do you have any more questions? Is that good, David? Okay, you're welcome. Okay, so so we now completed 4. We went over 4, we went over 1, we went over 2. The next question was about number 3. Can we do 3? Okay, so next one is 3. So suppose x, y takes some values in the square, 0, 2, 1, 3. With joint PDF, fx, y equals 7/2 x cubed y. Find the marginal PDFs f sub x, x, and f sub y, y. Okay, so let's find these marginal PDFs. Let's go to the whiteboard. So we have f sub x of x. So f sub x of x, right, are the sum over all values of, let me just check the problem for seconds. It takes x, y takes on values in the square. So x is a continuous random variable because all the points in the square are kind of a continuous nature, right? So we're going to integrate over y of f of x comma y dy. And when we integrate with respect to y, we're going to integrate over possible values of y. Well, the square is from 0 to 1, 3. So it's from 0, 2 to 1, 3. So it's 0, 2, 0, 2, 1, 3. So what we care about is this region. Okay, from 0, 2 to 1, 3. So these are x values and these are y values, right? Okay, so if we're integrating over y, we want to integrate over all y values. So if we fix x, right, if we fix an x value, then we want to kind of accumulate, we want to look over all y values. And so the y values range from 1 to 3. And so we're going to integrate from 1 to 3 with respect to y because we're integrating over all y values in this region for a fixed value of x. And so this is equal to def integral from 1 to 3 of what is f sub x? What is the joint? It's 7/2 x cubed y. 7/2 x cubed y dy. So this is equal to 7/2 times x cubed because it's a constant. And now the only thing that isn't a constant is y. So it's integral from 1 to 3 of y dy. And that's equal to 7/2 x squared. And then the y becomes y squared over 2 as an antiderivative evaluated from 1 to 3. And then when you do that, the 1/2 moves out. So you get 7/4 x squared. And then multiplied y squared from 1 to 3, that's 3 squared minus 1 squared. That's 3 squared minus 1 squared. And so that's equal to 3 squared minus 1 squared is 9 minus 1, which is 8. 1/4 times 8 is 2. 7 times 2 is 14. So you get 14x squared. So what we got here is that f sub x of x is equal to 14x squared. Now f sub y of y is then equal to the integral of f of x comma y dx. So we're finding the probability that y is a fixed value. And so here we want to fix y. We want to fix y and that's a horizontal line. We want to fix y, and we want to integrate over all the possible values x for a fixed y, and so that's from 0 to 2, because x ranges from 0 to 2 for a fixed value of y. And so now that's equal to, and so what we're doing here is we're finding f sub y of y, and so the orange is going to correspond with this orange, and this pink is going to correspond with that pink, okay? Because you have to remember whether it's vertical or horizontal, and so I'm using the colors here to help you correspond the two, right? Which one was for which? That could be confusing. Okay, so then this is definitely from 0 to 2 of f of x comma y, which is still 7/2 x cubed y, but now it's dx. So this is equal to, well, 7/2 y is a constant. And now we're integrating from 0 to 2 of x cubed dx. And so that's equal to 7/2 y times integrate an antiderivative of x cubed is x to the 4th over 4, and we're evaluating it from 0 to 2. So the 1/4 moves out, and so you have 7/8 for 1/2 times 1/4 is 1/8. You have 7/8 y times, and now about x to the 4th value from 0 to 2 is 2 to the 4th minus 0 to the 4th power. And so then that's equal to 2 to the 4th is 16 minus 0 is 16. 16 times 1/8 is 2. 2 times 7 is 14. So this is 14 y. And so f sub y of y is 14 y. Okay, and so now those are the marginal probability functions, f sub x of x and f sub y of y. Okay, we go back to the whiteboard. Does that make sense? Are there any questions about that? Okay, if you still need to, you can think about this, look through it, right? Okay, so that's 1 through 4. So bring us at 6 and 7. Okay, 6 to 7 was first, and 6 was the first one asked between 6 to 7. So let's look at 6. Let x be a continuous random variable with that PDF. Find capital E of x. Okay, so capital E of x is just the integral. Let's use another color. Let's use purple. So here, capital E of x oh, it's capital E of x. Okay, so capital E of x is the integral of x f of x, right? Oh, and it's not x. Well, it's you're talking about x, but you need a dummy variable because you're going to integrate from negative infinity to that value of x. And so you're going to choose, so now you have the dummy variable t, f of t, dt. Okay. Oh, sorry. Okay, sorry. No, I mean you're integrating with x. Okay, so hold on. You're adding over all possible values of x, so it's not. I'm mixing this up with the thing I just taught. Okay, so there we go. Okay, so E of x is equal to integral from negative infinity of x f of x dx. Okay, so it's like for the discrete case when you add over all possible values of x times f of x. Here you're integrating over all possible values of x times f. Okay, so you just want to calculate this value for that PDF. Okay, so for that. Let's take this expression. Let's find e of x. And so for that, I'm going to go to the whiteboard. Okay, so 3 is on the whiteboard fully. 4 is on explained on the whiteboard fully. Okay, so next is number 6. And so for this, we have our PDF. So you hope to have the file in front of you yourself. This is beta e to negative beta. F of x is equal to the piecewise function beta e to the negative beta. This is if x is greater or equal to 0 and 0 elsewhere. Let me just check this again. Beta e negative beta x. X greater than 0 and 0 elsewhere. Okay, so we want to find e of x. Good, going down. Okay, okay, so e of x. Okay, so e of x is going to equal to the integral from negative infinity to infinity of this. Well, actually, if x f of x dx, that's equal to, so you have this. Now you substitute for f of x that. Wait, never mind. You substitute for f of x is this if x is greater than or equal to 0. So you only need x values greater than or equal to 0. And there, the PDF is beta e to the negative beta x, right? And so you just need to find the value of that integral. And so you have beta, which is a constant, times the integral, still from 0 to infinity, of x e to the negative beta x dx. And then that's equal to beta times the value of that def integral, right? And so we're going to use u substitution, where u is going to equal negative beta x. And so then that means that du is going to equal to negative beta dx. Okay, so we have a beta here already. So what we want is, if we have this integral, we have this integral and we have beta, but I want a negative beta. So I'm going to put a negative beta here and then a -1 here. So I did was I multiplied it by -1 twice. I have a -1 on the outside and a negative on the inside. This is the beta. I actually didn't really want to move beta in the first place, and so I'm wondering if I should just, what I'm going to do, I'm going to put the beta here. Okay, so I just moved the terms around, so beta's here. But then when I put beta here, I really need a negative beta dx. So I just multiply this by -1 and then have a -1 here. And then, so then the negative beta dx is du, and you have u is negative beta x. And so now you have the integral from, You have the integral from 0. Well, let me do u substitution. So you have -1. Okay, you have -1. And then if u is negative, this implies that if u is negative beta x, then this implies that x is u is negative u divided by beta. Right? Okay, because solving for x, we then divide by negative beta, and we get x equals negative u over beta. Okay, because I'm going to substitute that here. So x here is negative u over beta. So that is x. Then e to the negative beta x. Beta x is u, so this is e to the u. And then negative beta dx is du, so that's du right there. Oh, never mind, sorry. Back. It's integration by parts. We need to use, so side work, goal, you know what, find. So when you're computing integrals, sometimes the first thing you do, you realize you have to do something different. So find this using integration by parts. Okay, so now let's do that. So this is equal to, so I need to make this expression simpler. So the easiest way to make this expression simpler, the easiest way to make this expression easier is to let u equal x and dv to equal e to the negative beta x. Okay, and since we're not using u substitution and we're doing integration by parts, I'm just going to look at this. And when I look at this, I'm just going to, when I look at this integral, I'm going to move the beta outside of it. Okay, so this is equal to beta times this integral. And so I don't want that either. So we're just going to find this integral. We don't have the negative beta. Okay, so we have this, we plug in that, we move the beta out, and I want to find this integral using integration by parts. And so then, okay, so then the easy way, so let u equal x and dv equal e negative beta x. Then du is equal to dx, and then v is equal to antiderivative of e to negative beta x. That's negative 1 over beta e to the negative beta x. If you take the derivative of this, you get e to negative beta x times the derivative of the exponent, which is negative beta. So negative beta times negative 1 over beta is 1. And you get e negative beta x. So an antiderivative of dv, an antiderivative of e negative beta x is negative 1 over beta e negative beta x. Okay, and so that means that by integration by parts, this thing is equal to uv minus the uv evaluated from 0 to infinity minus the integral from 0 to infinity of b du is equal to, so u is x, v is negative 1 over beta e to negative beta x, not the equal sign. Okay, so that's UV, but then evaluated from 0 to infinity minus the depth integral from 0 to infinity of V, which is that, which is without the minus sign, du, which is dx. And so then this is equal to, so these are for x values. So when x is, so when x is infinity, so when x is infinity, let's look at this expression. When x is infinity, you have the limit as x approaches infinity of x times this expression, okay? Because this is plugging in for infinity. It's like double parentheses here. I don't want that. Just want what's inside the parentheses to be in that parentheses. Okay, so when you evaluate this, right, you have this at infinity minus that at 0. Well, what is this at infinity? It's really the limit as x approaches infinity. It's the limit as x approaches infinity, right? So this evaluate from infinity to 0 means this expression at plugging it at infinity minus this expression at 0. This expression at infinity is the same as the limit as x approaches infinity of that expression. Now you have a negative 1 over beta, which won't really matter much. And you can move this out of the limit. And so you still have the limit as x approaches infinity limit as x approaches infinity of, I just moved the negative 1 over beta out. So it's x e to the negative beta x, okay? That's the same as negative 1 over beta times the limits as x approaches infinity of x divided by e to the beta x, okay, because it's a negative exponent. And so now this is equal to, now if you take the limit of this over this, you end up using L'Hopital's rule in calculus. And so L'Hopital's rule will tell you that the limit, the denominator is just increasing much faster than the numerator. And so this is equal to the limit, but being specific, doing this rigorously by L'Hopital's rule, this is equal to the limit as x approaches infinity of 1 divided by beta e to the beta x. It's the derivative of the numerator divided by, it's the limit of the derivative of the numerator divided by the denominator, but that's by L'Hopital's rule, so it meets all the conditions of L'Hopital's rule. And so then this is equal to, well, the limit of the numerator is a constant, it's 1. The limit of the denominator is infinity, so the limit of 1 over this is 0. So you get negative 1 over beta times that limit, which is 0. And so that limit, I'm going to add parentheses here so that you can match the parentheses on the left with the parentheses on the right. So that limit is 0. Okay, and so now the product of negative 1 over beta times 0 is 0. So I knew this was going to be 0, but I did all this work to show you it was 0. When you evaluate this at infinity, you get 0, and then minus, plugging in x equals 0, it's 0 times anything, which is 0. Well, sort of 0, you plug in 0 here, and you get negative 1 over beta. So it's 0 times negative 1 over beta, which is 0. So 0 minus 0 is there. And then minus this integral here, but actually there's a negative sign here. So the negatives become a plus. And so this is plus 1 over beta times the integral from 0 to infinity of e to the negative beta x dx. Okay, and you evaluate this integral. Did I do this one? Maybe I didn't. Okay, so now I'm going to do it now. This is equal to 1 over beta times in there the value of this integral, right? So we're going to compute this integral here. And so an antiderivative negative e to negative beta x, maybe I think that maybe a negative 1 over beta is an e to the negative beta x. So you take the derivative of this expression, you get e negative beta x times negative beta times negative 1 over beta cancels. So this is an antiderivative of this integrand, and you're evaluating it from, all right, just as quickly, from 0 to infinity. And so now this is equal to, you have a negative 1 over beta as a constant. And then you have e to negative beta x value from 0 to infinity. At infinity, it's 0. Minus at 0, it's 1. And so this is equal to 1 over beta. So that expression is 1 over beta. So the thing that you plug in there is 1 over beta. And so this is 1 over beta. We got lots of betas, 1 over betas and betas. Okay, so you have 1 over beta squared. So this integral is 1 over beta squared. And well, this integral is this thing here. So this is beta times this, where this is, I'm going to put a bracket here so you can see that the thing that the bracket represents the value of that. You wouldn't put a bracket normally around here, but I'm putting it there so that this is equal to 1 over beta squared. And so this integral is 1 over beta squared, and so it's beta times 1 over beta squared, and that's equal to 1 over beta. And that's it. So e of x is 1 over beta. And so that's the answer. And so you need to do is read this over. You need to know calculus also. Okay, so that's number 6. Any questions about number 6? Let's keep going. Look, I'm going to go in order of the questions. So the person asked for 2 answers. So now I'm going to do a second. I'm now going to go to number 7, because that's in the order of being asked. Number 7, consider this experiment. Roll a die. If the outcome is a 4, select a number at random from the interval 0, 2. If the outcome is not a 4, select a number at random from the interval 2, 3, 3. Let x equal the value of the number selected. A, draw a histogram of this random variable, assuming x is rounded to 1 decimal place. Find the probability density function of x. Okay. Okay, so the probability histogram, right, is the thing that looks like bars. It's not the line. The vertical line is the bar chart, and then the histogram is where you have like these rectangles centered on the x-axis at those points. Okay, so you roll a die. Oh, okay, you roll a die. The possibilities of rolling a die. No, if you select a 4, select a number at random from the interval 0, 2. I need a new color now. Let's use brown. Okay, so you have a number between 0 and 2. That's if the outcome of the roll is a 4. So if you roll a 4, you choose a number between 0 and 2, strictly between 0 and 2 randomly. If the outcome is not a 4, select a number at random from the interval. So if it's not a 4, select a number at random from the interval 2, 3. X equal the value number selected. Draw a histogram of this random variable. Okay, and so we're going to round to nearest 1 decimal place. Okay, so what are the decimal places that matter? We have 1, and the 1 decimal place means tenths. So we have 20 tenths here and 10 tenths there. And so let's go to the whiteboard. Okay, so what were the, so 0 to 2, 2 to 3. 0 to 2, 2 to 3. So it's going to go up to 3. So putting the 3 there. This would be halfway. That'd be 1.5. So maybe like 1 here and 2 here to even this out. Okay, tenths. So this would be like the halfway point. This would be like 0.5. You have 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 0.10. This would be the 1.5 point. And so you'd have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then this is the halfway point here. So this is 2.5. And then 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so these are all 30 there. Okay, so the test is only an hour long. I'm not going to ask you a question that would take you a really long time. Draw a histogram of this random variable. Assume x is rounded to 1 decimal place. Okay, so select the number at random from the interval 0, 2. Okay, so if the outcome is a 4. Okay, so so the outcome is a 4, right? So we realize there's a 1/6 chance that you choose a number at random from the interval 0, 2, right? There's a 1/6 chance. Now, not only is there, so there's a 1/6 chance of starting in this interval from 0 to 2. Okay, so there's a 1/6 chance that you're somewhere between, you choose a number at random somewhere between 0 and 2. But now, if you look at any tenths, 0 is also a possibility. So it's rounded to 1 decimal place. Okay, so 0 is a possibility. Let's look at the space that's made up here. So if you look at the space made up in tenths, if you have 1, 2, 3, 4, 5, 10, 15, 20, you have 20 dashes here, right? 18 of them are in the middle. 2 of them are at the end, right? Now, rounding to the nearest decimal place means you kind of have like half of this. You kind of have like half of this region here. So you have 18 points in the middle and you have 2 at the end. The ones at the end take up half space because you can only round down or round up. So these, you have 18 plus 1, because this is a half and this is a half. So you have 9, you kind of have the split into 19ths. And so if it's split into 19ths, that means there's 1/19. It takes each, you kind of think of 1/19 of the space, and you have I'm not going to ask this problem on the exam. And then it's times 1/6 because there's a 1/6 chance of choosing something in that interval. And so you have 1 over 114. So you have 1 over 114. probability of being somewhere here. So I'm gonna, even though this 1/114 is not a large number, but we don't have that many options in this problem, so we can just go ahead and make this large enough to see. So now the bar, I don't want that to be mixed up with the bars. I'm doing two different things here. This is the height. This is just noting where this is. This is going to go from here to here. So I'm going to draw a horizontal line on my screen. Okay, and so now the bar for this amount, this one, 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 this one. So you're not calculating 30 different values here. There's a few and they're repeated many times. Okay, so now the height of each bar at 0.1, 0.2, 0.3 rounded to the nearest tenth is 1/114. Now, if you're at 0, oh wait, sorry. 18, 19, 1/19. Yeah, good. Okay. So 1/10 of the space makes up wait, no, okay, sorry, I made a mistake. I don't have to erase that much. Look, I don't have to erase that much, but just a simple way to say it. The height. This space that takes up half of a tenth and a half tenth, right? This takes up 1/10, right? The base here is 1/10 because you're rounding to the nearest tenth. And so that's 1/10. That's 1/10 of the that's 1/20th of the total space made up on the x-axis, right? Because there's a 1/10 in the base here. You're rounding to the nearest tenth, but you could round up or down because this makes up one. This is a unit 1/10 out of 2. So it's 1/20th of this total space. So when you choose a number randomly from 0 to 2, you have a 1/20th chance of it being rounded to any particular tenth here, one of these dashes. So 1/20th times 1/6, because that's the probability of choosing something there, that's 1/20. So we have a simpler number, it is 1/20. So this height is 1/120. Okay, now if you round it to 0, you only round down to 0. So if you only round down to 0, you only have half a tenth. It's only half a tenth of a chance. So you have one so you have half, so you have 1/20th, but it's out of 2, so it's 1/40th. This makes up half the space of an indent. See, it's halfway there. There are 20 indents, and so it's half of them. So there's actually, this thing from 0 to 2 is made up of 40 of these half indices. So this is 1/40th of the total thing. And there's a 1/6 chance you would choose that interval. So this is 1/240. There's a 1/240 chance that the number is rounded down to 0. So there's a 1/240 chance the number is rounded to 0. So the histogram will then have a height of 1/240 at 0. Oh, wait. The number is selected at random from the interval. Yeah. Oh, okay. Right. But it could be 0.00, it could be 0.00001, right? It doesn't have to be 0. It could still round down to 0, even though it's not 0 itself. Okay, so it rounds down to 0, even though you can't choose 0, it would round down to 0. So there's a 1 over 240th chance that it rounds down to 0. Now, there's also a 1 over 240 chance that it rounds up to 2, but when we consider it from 2 to 3, we could round down to 0 there, and we'll add it. So we're going to do that 2 last. Okay, so now if it's between 2 and 3, between 2 and 3, if it's between 2 and 3, there's, right, if it's not a 4, there's a 5/6 chance that when it's not a 4, you choose a number random between 2 and 3, right? So there's a 5/6 chance there. So there's a 5/6 chance you're somewhere like over here. Now, if you look at a 1/10 region, right? If you round to nearest 10, then you could either round up to nearest 10th or down. But the region takes up 1/10 space in a total interval of 1. So that's 1/10. So it takes up 1/10 of the total space, right, on the x-axis. This times 5/6 the chance you would choose it there in the first place. So 5 over 10 is 1/2. So this is 1 over 12. This is a 1/12 chance, which is much better than 1 over 20. That makes sense because there's a 5/6 chance you choose this interval, right? So there's a 1/12 chance that that you're there. Now you wouldn't use different. I'm not going to use different colors. So all the way up here, I'm going to have the number 1/12. Okay, it's not proportional. So for 1/12, there's a 1/12 chance that you would round to these middle dashes. But keep in mind that I'm not counting 3 right now. I'm only talking about, and when I calculated each of these, I took each individually into account. So I don't have to worry about not looking at 3 yet. Okay, so this is the bar chart. So this is the histogram so far. So now, if you look at the number 3, right? This takes up, you only round up to 3. You can't choose 3, but you could choose a number close to 3, so it rounds up to 3. So this takes up a half of a thing here between lines. There are 10 of those, so it's half of that. So this is 1/20th of the space. So if it makes up 1/20th of the space, and there's a 5/6 chance you would choose a number there in the first place, 5 over 20 is 1/4. 1/4 times 1/6 is 1 over 24. That's half of it, right? So now there's a 1 over 24 chance, which is much larger than 1 over 120, 5 times as large, that you would end up here. And so then that height is the probability associated with the 3. Okay, so the probability of rounding only up to 3 is 1 over 24, and then the probability of either choosing a number between 0 and 2 or rounding up to 2, or probably choosing a number between 2 and 3 and rounding down to 2, you'd add these two probabilities. So first, there's a 1 over 24 chance that you round down to 2, just like you would round up to 3. Okay, so there's a 1 over 24 chance you would round down to 2. There's also a 1 over 200. There's also just like there's 1 over 240 chance you would round down to 0. There's a 1 over 240 chance you round up to 2. And so I'm going to now put a pink thing here and a pink thing here and say that this bar is the sum of those two probabilities. And so 1 over 24 plus 1 over 240, that's the same as 10 over 240 plus 1 over 240. And so that's 11 over 240. And so it's only slightly higher than this one, but I'm just going to exaggerate it. This is 11 over 240. And this height is the height of this of 2. It's a little bit, it's more likely than this one and less likely than the other one. And it's there. Okay? So that is the probability histogram for that one. And then for B, it's just find the probability density function of X. And so I basically did that in the example. I told you that, I'll write it down. I told you f of X by the heights of the graph that I found. I found the PDF, and so f of X is equal to, f of X is going to equal, the probability is 1 over 120. It's 1 over 240 for X equals 0. So it's 1 over 240 for X equals 0. And it's 1 over 120 when X rounded to the nearest tenth is either 0.1, 0.2, up to and including 1.9. Okay, so this is going a while, but you're asking questions, right? So you want me to keep going, right? So this is 1.9. Okay, now the probably X equals 2 is 11 over 240. Okay, then X is 2.1 to 2.9. When I did the answer sheet to this, I may have simplified the problem by ignoring the fact that you round up and down and just said, don't worry about it. This is perfect. So you can go by this. 2.1 to 2.9 is 1/12. Okay, and then probably X equals 3 is 1 over 24. Okay, so you wanted all the numbers rounded to the nearest. So it was all numbers rounded to the nearest tenth. 0.1 to 1.9, 2, 2.1 to 2.9, 3. So those are all the possibilities. And if you add them all up, that should add up to 1. Because if we're looking at 240, there's 1 240 here. There's 2 for each of these, and there's 19 of them. So that's 38, 39. I'm just going to add them up to myself. I really hope it adds up. This is 2. That's 11. So there's another 11 there. There's 9 here, but each of them are 20. So that's 9 times 20. That's 180. And then this is 10 of those because it's 1 over 240, so it's 10. And this should add up to 240. Looking good so far. 3, 4, 5, 6, 14, 240. It worked perfectly. That's absolutely right. Good. When you have all those numbers moving around, you know, that was right. It added up exactly 240. Good. So that's the PDF for number histogram and PDF for number 7. So that's for number 7. So this is number 7. Okay, and this is still number 7. I'm just gonna write number 7 so that this is part B for number 7, actually. So I can label 2 different things and make more sense. And then the other page was part A for number 7. This A has to do with the number, not the bar chart. I mean, not the histogram. Okay, so that was the histogram and the PDF for number 7. Okay, and then someone said number 5. So let's do number 5 since you asked. So you want me to keep going. So that's why this is this lesson is going very long. You want me to keep explaining things. Number 5. It's number 5. I'm going to keep with the. Actually, am I going to use the whiteboard? Maybe not. Suppose that a point x and y is selected at random inside the circle with radius 3 and center 0, 0. Find the joint PDF of x and y. Okay, yep, we're going to do that. Okay, so radius 3 centered at 0. Radius 3 centered at 0. Why was it? I don't think I was holding my hand down. Okay, I wanted that. Okay, now there's the circle. Radius is 3. Okay, so what they want in the problem, go back again, find the joint PDF of x and y. You choose a point at random from inside the circle. Find the joint PDF of x and y. This is the origin, right? The point 0, 0 is the origin. Okay, and so just the PDF of x and y is equal to 1 over the amount of space that circle makes up. And so how much area does a circle make up? The area of that circle is equal to pi r squared, where the radius is r squared, where the radius is 3. So this is equal to pi times 3 squared. So this is 9 pi. 3 squared is 9. So this is 1 over 9 pi. So the joint probability density function is 1 over 9 pi because it's 1 over the area that the circle makes up. Okay, so this circle makes up that much area. Okay, and so the PDF has to be 1 over that area. That's number 5. So number 5 is very easy. And there you go. That's every problem on the practice question sheet. Okay, I'm going to save it. Okay, so I wrote a bunch of stuff down here. So what I'm going to do is I'm going to, if I can, if it lets me, I know sometimes computers are weird. I haven't done this yet for this class. I'm going to try to upload this onto today's folder. Okay, so I'm going to put it in today's folder. I'll also put it in the test 2 folder if I can. Okay, if I can, I'm going to put this file in today's lesson folder and in the test 2 folder. Okay, so we are done with today. Before I forget, I'm going to save the whiteboard as a PDF, and I have the folder there. Okay, so I have the whiteboard. Okay, so we're going to stop here. I have all the announcements already in the lesson, so make sure to remember all of that that's in the lesson. Okay, and I'll see all of you tomorrow morning. Okay, thanks for asking questions, and good luck on the exam tomorrow. Okay, bye. You're welcome. You're welcome. See you tomorrow. You're welcome. Bye. You're welcome.